Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 45 on sequences.
We now begin the last chapter of our course, where we build a discrete calculus, reinventing everything that we've done so far for functions with a digital input. These functions, or sequences, will be familiar objects to you from throughout the course, but we'll look at them from a new perspective of discrete calculus.
Everything that we have done thus far in this course has been for functions that might be described as analog. They are functions whose inputs and outputs, with few exceptions, vary continuously, if not smoothly. This allows us to talk about limits, differentials, and build up calculus. In contrast, so much of what we see and build is digital and not analog, built of discrete or quantized bits, whether it's music, imagery, or information. Many things are not amenable to smooth calculus. For this reason, we're going to reconsider the notion of a sequence. We've seen sequences before, but here's a slightly different perspective. A sequence is a discrete or digital input function with an analog output. That is, the inputs are natural numbers, the outputs are reals. Now, sequences are everywhere, from economic data to digital signals. But thinking of them as a function with an input, say n, and an output a sub n, is going to be the focus of this chapter. The notation that we'll use sometimes is writing out the terms of the sequence, that is the outputs, a sub 0, a sub 1, a sub 2, etc. Now our goal is going to be to redo everything that we have done in this calculus class, but in a digital form or a discrete form for functions with a discrete input, that is, for sequences. All of the many things that we have discovered so far have digital images in this discrete calculus. We'll begin, as we began this course, with examples of interesting functions or sequences. For example, there are many sequences that are polynomial, like n squared. Other sequences do not grow like a polynomial, but are rather exponential, like the sequence 2 to the n. How would you describe the sequence 1, negative 1, 1, negative 1, repeating? Well, it seems a little odd at first, but one could describe this as a trigonometric function, for example, as cosine of n times pi. Now, more interesting sequences are out there. For example, what if we remove the pi and consider the sequence cosine n? If we plot the terms of that sequence as a function of n, we see a curious mixture of wave-like behavior, but non-repeatability. The sequence never repeats, and in that way it's a little bit unlike the trigonometric function cosine. This phenomenon is rather curious. You've seen it before if you've ever seen an object that spins so fast that your visual refresh rate can't keep up with it, and it looks like it's spinning at a different rate or even in a different direction. This is sometimes called aliasing. Let's begin our construction of discrete calculus with the notion of a limit. Now, what does it mean to take the limit of a sequence? Well, I believe our adventure begins with failure. Because of the discrete input, it doesn't make sense to talk about getting as close as you want to n equals 11. The one circumstance under which it does make sense is to take a limit as n goes to infinity. in this setting, then the original definition of the limit as n goes to infinity makes sense. We say that that limit is L if for every epsilon we find some value, let's say capital M, past which the output of the function lies within epsilon of the limit. This has to continue for any value of epsilon that is desired. As we change the tolerance on the output, we can find a new tolerance on the input in order to satisfy the condition. So with that in mind, why would we bother taking limits of sequences? Well, you've done so already in the context of Taylor series and approximation. We began this very course with the discussion of what E was in terms of the limit of a sequence. E is 1 plus 1 plus 1/2 plus 1/6, and each of these finite sums can be thought of as a term in a sequence whose limit is E. At other times in this course, we've implicitly assumed that we can take a limit of a sequence. We did so in Newton's method, where we glibly stated that we hope the limit of this sequence of points converges to the root that we were looking for. Now, all of this is good motivation, but how does one compute limits? The principle that we'll see over and over again is that one can use continuous methods to solve discrete problems. Let's see a simple example. Consider the sequence a sub n equals 1 plus alpha over n to the nth power. You've seen this before in the context where n is x, a continuous variable. Solving for the limit as n goes to infinity follows the exact same method. We take the log of both sides, pull that log inside the limit, and use it to remove the exponent n out in front. Then we use our knowledge of Taylor series to expand that logarithm as alpha over n plus big O of 1 over n squared. And this is the key point, that our use of Taylor series and big O works just as well in the discrete setting as in the continuous. And so we can evaluate the limit, exponentiate, and get an answer that should be very familiar. Another example would be a sub n equals 2n squared minus n square root of quantity 4n squared plus 5. We would attack this by doing some algebraic manipulation, factoring out a 2n squared. What is left is of the form 1 minus square root of 1 plus 5 over 4n squared. Here we see another Taylor series lurking, that involving the square root. Using the binomial series, we can obtain, after a little bit of algebraic simplification, that the leading order term is negative 5/4. Everything else is in big O of 1 over n squared. And so when we take the limit, we obtain negative 5/4. Now, not every limit is so transparent. For example, what would you do if asked to evaluate something of the form square root of 2 plus square root of 2 plus square root of 2 plus square root of 2, etc., all nested? Well, the appropriate way to handle something like this is to realize it as the limit of a sequence where we build things up step by step, beginning with root 2, and then with root 2 plus root 2, etc. We want to compute the limit of this sequence, a sub n. Now, in order to do so, there's one difficult and critical step. That is, you need to determine the recursion relation that the terms satisfy. In this case, I'll tell you that it is the following: a sub n equals square root of 2 plus a sub n minus 1. Let's say I give you that recursion relation. How do you compute the limit? Let us, as before, denote this limit by L, and then apply the limit to the recursion relation. On the left, we have the limit as n goes to infinity of a sub n. That's L. On the right, we have an a sub n minus 1 term. What's the limit of that as n goes to infinity? Well, of course, it too must be L. Now we're assuming that we can slip that limit in under the square root. Let's forget about whether that's legal or not and see what happens when we try to simplify this algebraically. Squaring both sides, we obtain L squared equals 2 plus L. With a little bit of rearrangement, we get a polynomial that easily factors into L minus 2 and L plus 1. Now this polynomial has two solutions, namely -1 and +2. We know that the limit of this sequence is not a negative number, and therefore, if the limit exists, it must be equal to 2. Indeed, the limit does exist and is 2. Let's look at another limit of this form. In this case, 1 plus 1 over 1 plus 1 over 1 plus 1, etc., all nested together. As before, we can write out a sequence that gets closer and closer to this. A naught is 1, A1 is 1 over 1 plus 1, A2 is 1 over 1 plus 1 over 1 over 1, or something like that. I don't know. It keeps going. The tricky part in this case is to find the recurrence relation that these terms satisfy. Once again, I'm going to tell you what it is. It is that a sub n equals 1 plus 1 over a sub n minus 1. This instruction tells you how to build the next term. In order to compute the limit of the a sub n's, we follow the same procedure as before, taking the limit of the recursion relation, substituting in L for a sub n and a sub n minus 1. And then, with a little bit of algebraic rearrangement, what do we see? We get L squared minus L minus 1 equals 0. This has roots 1 plus or minus square root of 5 over 2. One of these is negative, the other positive. We'll take that positive square root, and that is our limit. This particular value is of some independent interest. It is sometimes called the golden ratio, and given the symbol phi, it equals 1 plus root 5 over 2. Now, perhaps you've seen the golden ratio before in the context of some other sequences. Perhaps you've seen the Fibonacci sequence that begins with 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, etc. There's a lot of interesting mathematics hiding behind here. If you'd like, you might want to take a look at the bonus material for a hint at what calculus will be able to tell us about the Fibonacci sequence.
We began this course in calculus with the discussion of functions and a contemplation of the exponential function. In the same manner, we've begun our construction of the discrete calculus by considering functions or sequences. In our next lesson, we'll look at the discrete analog of the exponential function and see how it relates to derivatives.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 45, Bonus Material. In our main lesson, we considered sequences as the discrete version of functions, ending with a particular sequence due to Fibonacci and its relation to the golden ratio. That's what we're going to explore here. The Fibonacci sequence is a sequence. We'll denote it f sub n, and it is defined through the recursion relation. F sub n plus 2 equals f sub n plus 1 plus f sub n. And so beginning with the first two terms, 0 and 1, one computes the remaining terms by summing up the previous two. Now, people have found the Fibonacci sequence hiding in all sorts of natural objects. That's not really our concern in this class. We're going to stick to the math. And what kinds of mathematical things can we observe? Well, one is that the limit of incident terms in the Fibonacci sequence approaches phi, this golden ratio. That is, the limit as n goes to infinity of fn plus 1 over fn equals 1 plus root 5 over 2. How do we prove that? Begin with the recursion relation. Fn plus 2 equals fn plus 1 plus fn, and divide all terms by fn plus 1. This simplifies the middle expression to a 1. Call this limit of incident terms L, and then compute the limit of everything that we have. Now, on the left, you'll see fn plus 2 over fn plus 1. That, of course, is going to limit to the same thing as fn plus 1 over fn. That is L. On the right, we have something that will limit to 1 over L. And so we obtain the expression L equals 1 plus 1 over L. By multiplying through, we see a familiar quadratic expression that factors with roots phi and psi, where psi is 1 minus root 5 over 2. Now that, again, is a negative number. It's equal to 1 minus phi. In fact, we know that that is not the limit, and so the limit is phi, this golden ratio. Now, this still doesn't really feel like calculus, even though we're supposed to be doing discrete calculus at this point. Let me tell you what calculus is good for. Let's say you are asked to compute an exact expression for the Fibonacci number, or maybe an approximation. Let's say, what is the 1,000th Fibonacci number, or the 1,000,000th? Well, of course, you could get there by adding many times over, but there's a more intelligent way, using calculus. The solution that we'll present in a few lectures is that f sub n is exactly equal to 1 over root 5 times quantity phi to the n minus psi to the n, where phi and psi are as computed before. 1 plus root 5 over 2 and 1 minus root 5 over 2. Now, since the latter is negative, when we take a high power of that, it's going to be something that is negligible, very close to 0. And so we could approximate the nth Fibonacci number by phi to the n over square root of 5. That is a very convenient result. It's not hard at all to do that computation. This is one of the things that we'll see discrete calculus is good for. It's going to take a little bit of time to get to the point where we can do this. We have to build up some of the rest of our techniques involving discrete versions of derivatives and differential equations. We'll move on to discrete versions of integrals. Stay tuned and keep your eyes open for interesting sequences. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 46 on differences.
We begin our construction of a discrete calculus by building the notion of a derivative for a sequence. This definition is going to turn out to be much simpler than that of a derivative for a smooth function, but this simplicity hides a profound depth that mirrors all the things we have learned in calculus thus far.
Recall that our goal is to build a discrete calculus based on sequences. In this lesson, we'll consider what we mean by derivatives. This will come in the form of differences or finite differences. The definition is as follows. Let's say that you have a sequence a sub n. We say that the forward difference of a, delta a, at n is equal to a sub n plus 1 minus a sub n. That is, you look at the person in front of you and subtract off your present value. Now, if we compare this to the definition of the derivative, we see that there are some commonalities. We're taking a difference in the output of the function, dividing by a difference in the input of the function, in the case where that difference is equal to 1, because we're talking about a sequence. Now, if we were to try to graph this function and give an interpretation in terms of slope, then by connecting the dots, well, this would be the slope of the line segment in front of you, hence the forward difference. This motivates the definition of the backward difference. If you look behind you and consider the slope of that line, we define the backward difference, nabla a at n, to be a sub n minus a sub n minus 1. Let's consider a few examples. If we take the sequence 4n and compute its forward difference, what do we obtain? I'm going to leave the verification of the computation to you, but I want you to show that one obtains the constant sequence 4. Now, what do you observe here? It's as if we're taking the derivative of a linear function and obtaining the constant function. But here, these are sequences and differences instead of derivatives. Here's another example, a bit more interesting. The Fibonacci sequence. What happens when we take the forward difference of that? One finds that again, one obtains the Fibonacci sequence, but shifted over by one step with an additional 1 out in front. That seems like it must be significant. For our last example, consider the sequence 2 to the n. What happens when we compute the forward difference of that? We obtain, again, 2 to the n. It's as if this is something like the exponential function e to the x, which is its own derivative. But here, we're in the discrete world, taking differences. There are many parallels between differences and derivatives. For example, if we ask the question, which sequences are polynomial? Consider n squared. When we take its forward difference, we obtain a sequence of odd numbers. That is, the sequence 2n plus 1. What happens when we difference again? The second forward difference, delta squared, is, in this case, a constant, the constant sequence 2. What happens when we take the next difference, the third forward difference? Then we obtain the constant sequence 0. This is very similar to what happens when we differentiate a polynomial. After a finite number of steps, we get 0. In general, one can say that a sequence A is a polynomial of degree p if the p plus first derivative, that is, difference, of A is the constant 0. Now notice that there's something that's not quite according to what you would expect here. That is, the difference of n squared is not 2n, but rather 2n plus 1. Now that seems anomalous, but we can explain that with a bit more notation. In particular, that of the falling powers. These are discrete calculus versions of monomials. We say that n to the falling k is n times n minus 1 times n minus 2, all the way down to n minus k plus 1. That works for k bigger than 0. For k equal to 0, we'll define n to the falling 0 to be 1, of course. Now, the reason why this is so useful is that the forward difference of n to the falling k is k times n to the falling k minus 1. Let's look at this in the context of the example that we've done. Consider the sequence n squared. We could rewrite n squared as n times quantity n minus 1 plus n. That is, it's really n to the falling 2 plus n to the falling 1. And hence, the forward difference of n squared is the forward difference of n to the falling 2 plus n to the falling 1. Differencing, like differentiating, is linear. Hence, this is the difference of n to the falling 2 plus the difference of n to the falling 1. That is 2 n to the falling 1 plus n to the falling 0, otherwise written as the sequence 2n plus 1, which is what we observed. Now that seems a bit complicated. Why would you want to do that? Well, let's consider a more fundamental question. The question that began this course. What is E? Well, we know that E is 1 plus a half plus a sixth plus a 24th, etc. That is, the sum, k goes from 0 to infinity, of x to the k over k factorial, evaluated at x equals 1. Now, that's for smooth calculus. What about discrete calculus? What is the discrete version of E? Let's try the same thing, but using the discrete version of x to the k, that is n to the falling k. Consider the sum, k goes from 0 to infinity, of n to the falling k over k factorial, evaluated at n equals 1. What is that? Well, that's 1 plus n plus 1/2 n times n minus 1 plus 1/6 n times n minus 1 times n minus 2, etc. What happens when we evaluate this at n equals 1? Most of the terms vanish. All of the terms vanish, except the first two. When we evaluate at n equals 1, we get 1 plus 1, which, as you know, is equal to 2. Therefore, in discrete calculus, E really takes on the value of 2. And in fact, if we look at the version of e to the x, that is, the sum of n to the falling k over k factorial, we get precisely the sequence 2 to the n. And this is why, when we observed that the forward difference of 2 to the n is 2 to the n, it reminded us of the behavior of e to the x. At this point, you may feel a bit like Alice in Wonderland. What is with discrete e and 2 to the n and falling powers? Discrete calculus can be a strange place, but there is a more rigorous approach that you may find assuring. This approach uses the perspective of operators. These are things that transform functions into functions, or in this case, transform sequences. Some of these operators you've met before. For example, the identity operator. It acts on sequences in the way you expect. It does nothing. The identity applied to A, that is I of A, is the same sequence, A. What's nice about operators is that we can work with them algebraically. We can say that I squared, That is, applying the identity twice is the same thing as applying the identity once. It does nothing. E is the left shift operator. That is, E of A is the sequence which, in the nth slot, gives you A sub n plus 1. And again, we can take powers of E to shift further to the left. If there's a left shift, then there must be a right shift. This has the notation E inverse. It undoes E. Now we can take powers of this operator as well and start multiplying them together. They behave in the way that you would expect. E inverse E gives you E to the 0. That is the identity operator, I. That works as well. If you reverse the order, it doesn't matter. A few other operators that we've seen are the forward difference and the backward difference. We can write each of these in the language that we've already built. The forward difference, delta, is E minus I. The backward difference is I minus E inverse. You'll want to have these two formulae memorized. But why are they important? Here is an application to higher differences. Let's say you want to compute the second forward difference of A at n. This is the forward difference of the forward difference of A. That is the forward difference of A sub n plus 1 minus A sub n, which, with a little simplification, gives A sub n plus 2 minus 2A sub n plus 1 plus A sub n. What do you notice about those coefficients? Well, if we rewrote the difference operator as E minus I and square that, then, using the algebra of operators and simplifying according to what I does, we obtain E squared minus 2E plus I. That's simple. In more generality, if we have the kth forward difference, then by multiplying out E minus I k times, we can obtain the formula. The sum as I goes from 0 to k of negative 1 to the k minus I times the binomial coefficient k choose I e to the I. Now, this means what? Let's say that you wanted to compute a high difference. Let's say the 8th forward difference. That's going to depend on a lot of terms. What is the coefficient in front of the A sub n plus 6 term? Well, by writing down Pascal's triangle and looking up the appropriate coefficient with the minus sign in the right place, we easily see that that coefficient is negative 56. That is much simpler than trying to work it all out by hand. There are other things that we seem to be able to do as well. Consider the discrete notion of an indefinite integral. If the forward difference is E minus I, then what happens when we try to take the inverse, that is, undo differencing? Well, we need to take E minus I to the negative 1 power, let's say. If I wrote that a little bit differently, say put a minus sign out front and called it I minus E, then it is as if we're trying to compute 1 over I minus something. Well, I've seen formulae for 1 over 1 minus x in terms of a geometric series. What happens if we tried applying the geometric series to this formula? It would suggest that the inverse operator to forward differencing is minus I plus E squared plus E cubed plus E to the 4th, etc., etc. Now, that seems rather dubious. Let's check it on a simple example, see what we get. Let's take a random sequence. Let's say 3, negative 1, 4, negative 1, 5, negative 9, 2, negative 6, 5. and I'm tired, so I'm just going to write zeros from now on. What would this delta inverse really mean? It means what? Well, I need to, at the nth term, take the sum of all the terms in A that follow from n on up, and then put a minus sign in front of it. If we do so, walking down the line, we can, marching from the right, certainly compute the terms in this sequence. This is easy since our sequence terminated in zeros. What happens when we take that and forward difference it? I'll leave it to you to check that we obtain the original sequence A, that this actually does work. Now, don't get too carried away. You have to be careful. First of all, you forgot the constant. We all forgot the constant. Also, notice that this is only going to work if your sequence terminates in zeros, or rather is summable to the right. Have fun with discrete calculus, but be careful.
We've seen how finite differences provide a discrete version of a derivative for sequences, complete with interesting analogs of the exponential function and a surprising way to do anti-differencing. In our next lesson, we're going to go fully digital and use our notions of differencing and anti-differencing to give an overview of the discrete calculus.
Welcome to Digital Calculus. I am your synthesized, digitized Professor Greist. We're about to begin Lecture 47 on the discrete calculus. In our last two lessons, we have covered sequences and a discrete form of differentiation that works on sequences. In this lecture, we're going to go fully digital and build a discrete calculus for sequences. The discrete calculus mirrors the differential calculus in the following ways. The discrete version of a function is a sequence. The discrete version of a derivative is a difference. The discrete version of an integral is a sum. And the discrete version of a differential equation is a recurrence relation, also called a recursion relation. Let's start with something big, something fundamental. The fundamental theorem of integral calculus has a digital form. It takes the form of the sum as n goes from a to b of the forward difference of a sequence u is equal to that sequence u evaluated from n equals a to n equals b plus 1. Now, what does that mean? That means you evaluate the antiderivative, that is the antidifference, at the endpoints. But notice that there's a little bit of a difference here. We have to add a plus 1 to the upper limit. That's in the case of a forward difference. For a backwards difference, there is 1 subtracted from the lower limit. Now, what's the proof of the fundamental theorem of discrete calculus? Well, let's move this sum up and expand out exactly what it means. Remember, the forward difference says we take the next term in the sequence minus the current term. So if we add up all of the forward differences as n goes from a to b, then what do we see? We see that most of the terms cancel because you have a plus and then a minus of the same term. The only things that do not cancel are the first term, negative u sub a, and the last term, plus u sub b plus 1. And that is, indeed, as we have written it, the sequence evaluated at the limits. Now, sometimes these kinds of sums are called telescoping sums. But if you ever see reference to that, now you know you're really seeing the fundamental theorem in disguise. Here are a few examples of the fundamental theorem of discrete calculus in action. Since the forward difference of the sequence 1 over n is equal to, by definition, 1 over n plus 1 minus 1 over n, which, when simplified, is negative 1 over n squared plus n. Then we can, if you like, integrate both sides to obtain an explicit formula for the sum as n goes from a to b of 1 over n squared plus n. It is the antiderivative, if you will, negative 1 over n evaluated from a to b plus 1. This can be written with a little bit of algebraic simplification as b minus a plus 1 over a times quantity b plus 1. Here's another example. Since the forward difference of the sequence n factorial is, by definition, n plus 1 factorial minus n factorial, which, after factoring out an n factorial, gives n factorial times n. Then we get an unusual-looking formula. The sum as n goes from a to b of n factorial times n is equal to n factorial evaluated from a to b plus 1. That's simply b plus 1 factorial minus a factorial. Very, very simple. Now, since we know a few things about the differences of falling powers, we can say some stronger things. For example, the sum as n goes from 1 to k of n. We've seen that sum before. Here's a way to get it by means of integration. This is really the sum of n to the falling 1 power. What's the antidifference of that? Well, it's 1/2 n to the falling 2. When we evaluate that from 1 to k plus 1, we get k plus 1 times k over 2. Now, you've seen this formula before, but I bet you've never seen this simple derivation. Here's one that's less obvious. The sum as n goes from 1 to k of n squared. We can rewrite n squared as n to the falling 2 plus n to the falling 1. We know how to anti-differentiate these falling powers, and so we get 1/3 n to the falling 3 plus 1/2 n to the falling 2 evaluated from 1 to k plus 1. I'm going to let you do the algebra here to obtain the final answer of k times k plus 1 times 2k plus 1 over 6. By reversing the product rule for forward differencing, it's possible to obtain an integration by parts formula. Here's what it looks like. The sum as n goes from a to b of u times the forward difference of v is equal to u times v evaluated from a to b plus 1 minus the sum from a to b of ev, the forward shift of v, times the difference, delta u. I'm not going to go through a proof of this. We'll leave that to some homework problems. Let's just do a simple example. The sum as n goes from 0 to k of n times 2 to the n is equal to what? Well, let's let u be equal to n, because I know what the forward difference of that is. That's simply 1. And we're going to let dv, and hence v, be the exponential sequence, 2 to the n. Now, in this case, what does the integration by parts formula tell us? It tells us that this sum is equal to u times v, that is n times 2 to the n, evaluated from 0 to k plus 1, minus the sum of the forward shift of v, that's 2 to the n plus 1, times the forward difference of n. Well, that forward difference is simply 1. And so we get, when we evaluate that middle term, k plus 1 times 2 to the k plus 1 minus 0. Then we have to subtract the sum from 0 to k of 2 to the n plus 1. That sum is not so bad. We know how to do that. We get, after a little bit of algebra, the final answer of k minus 1 times 2 to the k plus 1 plus 2. This is a highly non-obvious result and a good example of integration by parts. Let's turn to differential equations. These are recurrence relations, or sometimes recursion relations. The shift operator E acts something like a derivative in discrete calculus. Let's look at a linear first-order recurrence relation. This is something of the form u sub n plus 1 equals lambda times u sub n, where lambda is a constant. Now we can rewrite this using the language of operators as EU equals lambda times u. Or moving the lambda u over to the other side and factoring out the u, we have the operator E minus lambda I applied to u equals 0. Now, it's obvious what the solution to this recurrence relation is. U has to be some constant times lambda to the n. Why is that? Just look at the recursion relation. Un plus 1, the next term, equals lambda times un, the previous term. What is that constant, big C? Well, of course, that is the initial condition for the, quote, differential equation. It is u naught, a constant. So, at each step, you're simply multiplying by lambda. That is the simplest differential equation in discrete calculus. Now, if we change things just a little bit and look at a linear first-order difference equation, this is something of the form delta u equals lambda u. Now, using what we know about operators, we can say, well, delta is really E, the shift, minus I, the identity. And so what we're really saying is that E minus I applied to u is lambda u. Can we solve this? Moving things over to the other side, we see that this difference relation reduces to the recurrence relation, E minus quantity, lambda plus 1 I, applied to u, equals 0. We already know the solution to this. It is constant times quantity, lambda plus 1 to the n. Now this is extremely significant. If we compare this to the differential equation x prime equals lambda x, we know what the solution is. It is the constant, the initial condition, c, times e to the lambda t. Now, compare what's happening here. This tells you why the exponential sequence 2 to the n is really the discrete exponential function. It is the solution to the difference equation, delta u equals u. In other words, it's the solution to this difference relation when lambda equals 1. But notice, according to our solution, it's lambda plus 1 to the n. And since 1 plus 1 equals 2, we see that 2 to the n is the proper version of e to the x in discrete calculus. Let's go back to the Fibonacci sequence. This comes from something like a second-order differential equation, really a second-order recurrence. Recall, the Fibonacci sequence satisfies f sub n plus 2 equals f sub n plus 1 plus f sub n. If we move everything over to the left-hand side of the equation and write out using operators, what do we get? E squared minus e minus I applied to f equals 0. If we consider that as a second-order polynomial and factor this, just like e was a variable and I were a variable, then what would we get? We would get e minus phi I times e minus psi phi applied to f equals 0, where phi and psi are those two constants related to the golden ratio that we see whenever we find Fibonacci. The solutions to this recurrence relation are built from solutions to the individual first-order pieces. That is, e minus phi applied to a sequence f1 equals 0, or e minus psi applied to a sequence f2 equals 0. You don't quite know why this is true yet. You'll learn that in multivariable calculus. But let's just follow the conclusion, namely that the first type of solution is of the form constant C1 times phi to the n. The second type of solution is of the form constant C2 times psi to the n. The general solution, as I have claimed, is really a combination of these primal solutions, these pieces. The Fibonacci sequence, f sub n, is of the form constant C1 times phi to the n plus constant C2 times psi to the n. What are these constants? Well, we know what the Fibonacci sequence is when n equals 0. The zeroth term is, of course, 0. Applying n equals 0 to our general solution gives C1 plus C2. We know that the next term in the Fibonacci sequence, f1, equals 1. That is, C1 times phi plus C2 times psi. This is a system with two equations and two unknowns. We can solve that for C1 and C2. C1 is equal to 1 over root 5. C2 is negative 1 over root 5. Applying that to our general solution for the Fibonacci sequence f sub n, we get an exact answer. F sub n equals 1 over root 5 times phi to the n minus 1 over root 5 times psi to the n. That's a pretty amazing result, one that comes from a little bit of discrete calculus. Well, that's the end of our introduction to discrete calculus. But that's by no means the end of the subject. There's a lot more to it, but it's not usually covered in a calculus class. I hope you've enjoyed this foray into the world of discrete calculus. I hope you didn't find it too confusing. I hope it was a little bit inspiring. But if it was confusing, don't worry. In our next lesson, we're going to move on to some more concrete applications. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 48 on numerical ODEs.
Let's retreat from the digital back to the analog world and see how the two relate. We have used our intuition for smooth calculus to tell us things about the discrete world. In this lesson, we're going to see how the discrete calculus helps us solve smooth problems, in particular, the problem of solving ordinary differential equations.
In this chapter, we've been using our intuition from differential calculus to understand discrete calculus. But the inference can run backwards as well. And in this lesson, we're going to use our discrete understanding to solve problems in differential calculus. In particular, we're going to consider differential equations. Recall some of the main classes. In the simplest case, one just integrates both sides of the differential equation. Others are not so easy, but if the equation is, say, separable, then again, we can integrate and solve. In more complex examples still, say a linear differential equation, we can apply an integrating factor. This is great, but it will not help us solve the general case. And indeed, at some point, calculus fails to help, and we have to turn to a numerical method for solution. We're going to focus on the initial value problem for an ODE of the form dx dt equals f of x, comma, t. We can think of that differential equation as defining a slope field in the xt plane that tells us how x changes with t, or at what rate. Now, given some initial condition, x naught, at an initial time, t naught, what we want to do is approximate the final value, x star, at some final time, t star. Now, we don't know the solution x of t, and we're not going to be able to use calculus to get that analytic solution. So what we're going to do is try to approximate that final value, x star, as best we can. To approximate, we're going to use sequences. Let's begin, first of all, along the time axis. We're going to write a sequence t sub n that goes from t0, t1, all the way up to t capital N, where t naught is the initial time and t capital N is our final time, t star. This is going to be a uniform grid, meaning that we have a step size h equal to the final time minus the initial time divided by capital N. We are likewise going to approximate the x values by a sequence x sub n, where x naught is the initial condition on x, and hopefully our final x value, x capital N, is close enough to x star that we have a good approximation. The simplest way to do this is called Euler's method. Perhaps you've seen it before, but we're going to look at it from a discrete calculus perspective. We're going to take our differential equation and discretize it using sequences, and instead of derivatives, differences, a literal quotient of differences. What does this mean? Well, if we consider at the nth time step, then on the right we have f evaluated at x sub n, comma t sub n. On the left, we have the quotient of differences. Delta x is xn plus 1 minus xn. Delta t is tn plus 1 minus tn. Of course, since we're using a uniform grid, that delta t is simply equal to h, our step size. And now, with a little bit of rearrangement, we obtain Euler's method. This is an update rule. It tells you that if you know x sub n and t sub n, you can obtain xn plus 1 as xn plus h times f evaluated at xn, comma, tn. That's the method, but what does it mean geometrically? Well, if we are at time step t sub n, and we have our approximation x sub n, we'd like to get to an approximation at tn plus 1. We don't know the true solution that passes through that point, but we do know the value of f there. That is telling us the slope. And what Euler's method is really doing is projecting forward to time t sub n plus 1. At heart, Euler's method is a linearization. So why does it work? Well, it works because we repeat this at each time step, linearizing and approximating as we move from time step to time step. Let's look at a simple example, a differential equation that we already know how to solve. dx dt equals x. We'll choose an initial time of 0, an initial value, x naught, equal to 1, a final time, t star, equal to 1. What is x star? Well, we already know that the solution of this equation is e to the t, and so x star really should be e. But let's see what happens when we choose a step size of h, that is, final time minus initial time over capital N. In other words, 1 over capital N. Euler's method tells us that xn plus 1 equals xn plus h times f at xn, comma, tn. What's f in this case? Oh, it's the right-hand side of the ODE, in this case just the x value. So we can simplify Euler's update rule to xn plus 1 equals xn plus hxn. Factoring out the xn, we get quantity 1 plus h times xn. Now, we've seen this before. This is really a recursion relation. E applied to the sequence x equals quantity 1 plus h times x. Now, you may recall from our lectures on discrete calculus that we know how to solve such simple recurrence relations. The sequence x is really x naught times quantity 1 plus h to the n. It is that coefficient of 1 plus h that determines the solution. This means that our final value, x sub capital N, is x naught times quantity 1 plus h to the capital N. If we substitute in 1 over capital N for h, then we obtain something that should look familiar. Quantity 1 plus 1 over capital N to the capital N power. You may recall that for n large, this is a very good approximation to E, our desired final value. What happens when we do an example, the answer to which we don't already know? Consider dx dt equals cosine t plus sine of x with an initial time of 0, an initial value of 0, and a final time of pi. I don't know what the final value should be. This is not a separable equation, and so we're going to fire up the computer, program in, let's say, 5 time steps, and see what it says. We will break up the time interval into 5 equal subintervals, and then use Euler's method to approximate what x sub 5 should be. And we get a value of about 2.4. Now, that's with 5 time steps. If we use a greater number of time steps, Euler's method will return, hopefully, a more accurate approximation to that final value. And as we move towards, let's say, 80 time steps, we seem to be converging. The final answer looks like it ought to be about 2.25, 2.24, something like that. It's hard to say without running more examples. Now, why is it that Euler's method works and seems to converge? How quickly does it converge? Well, we're going to think from a Taylor series point of view. Consider what happens when we expand the solution x of t about t naught. X of t naught plus h is, by a Taylor series, x naught plus h times the derivative of x with respect to t evaluated at t naught plus something in big O of h squared. Now, what's that derivative evaluated at t naught? That is simply f at x naught, comma, t naught. And here we see Euler's method hiding inside of the Taylor series. Euler's method is really just Taylor expansion and dropping all of the terms of order 2 and greater. Now, we say because of this that Euler's method is a first-order method, and that the error you make at each step is in big O of h squared, where h is our time step, remember. Now, what is the net error when you do capital N such steps? Well, it's capital N times something in big O of h squared. You might think, haha, capital N is a constant, so I can forget about it since we're doing big O. No, capital N depends on h. It's really some constant, the change in time, divided by h. And so, being careful, we see that the net error is in big O of h. We'll look at two other methods for doing numerical ODEs. The first is called the midpoint method. It begins easily enough, just like the Euler method. One projects forward. Call this change in x that we get from Euler's method kappa. Now, this is the midpoint method. So what we're going to do is take the time value that is in between t sub n and tn plus 1 and try to approximate what the differential equation is doing there. We will use evaluation at that midpoint to obtain a new slope and pull that back to x sub n and then project that forward at that midpoint slope to get x n plus 1. Now, when we write all this out algebraically, it involves this constant kappa, and it looks a little bit complicated. You don't have to memorize this, but what you do need to know is that this is a second-order method. That means that we're really doing a Taylor expansion and keeping all the terms up to and including degree 2. The step error in the midpoint method is in big O of h cubed, meaning that the net error is in big O of h squared. This is a better approximation at the expense of being algebraically more complex. Now, with that in mind, you might wonder, wouldn't it be possible to do higher order approximations using midpoints, pulling it back, and then evaluating again, pushing it forward, and then pulling it back, and averaging everything all up together? Indeed, this is possible, and this is a wonderful method called the Runge-Kutta method. There's a lot of equations that go into this. You don't have to memorize it. What you need to know is that, first, this exists, and second, it's very helpful, even if it seems rather mysterious. This is a fourth-order method. Very good approximation. Your step error is in big O of h to the fifth, and your net error is in big O of h to the fourth. Let's compare all these methods together in the one simple example that we know how to solve. dx dt equals x with the initial time 0, the initial value 1, the final time 1, and our final value, x star, which is known to be e. We've already seen what happens in the general case in Euler as h is going to 0. Let's be dumb. Let's use one step. We're going to take our step size h to be equal to 1. In Euler's method, what do we get? Well, we get simply that x1 equals 1 plus h times x naught. Since x naught is equal to 1, we get an approximation of 1 plus 1. That's not a terrible approximation to e, given that we've only done one step. But that's all we get from Euler. Now, with the midpoint method, our kappa value, we already know what that is. That is equal to 1. What happens when we take the formula for the midpoint method? Well, we get a value of x1 equal to 1 plus h times quantity x naught plus 1/2 kappa. That means we get 1 plus 1 plus 1/2. That's a better approximation to e. Finally, when we go all the way and write down all of those formulae for the Runge-Kutta fourth order method, then with a little bit of algebra, you'll see we get 1 plus 1 plus a half plus 1/6 plus 1/24. And now you see the pattern. These numerical methods are really just giving higher and higher terms from the Taylor series. The moral of our story is that by looking at things from a Taylor series point of view, you can understand errors.
We've now seen just a small taste of how discrete or digital methods help us solve smooth calculus problems. But this is by no means the only possible example. In our next lesson, we'll consider how to use the discrete calculus to solve problems involving definite integrals.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 49 on numerical integration.
In Chapter 3 of this course, you had a lot of practice computing definite and indefinite integrals. In this lesson, we're going to see how the discrete or digital calculus helps us to solve definite integrals. This is the beginning of the subject known as numerical analysis.
In this lesson, we'll continue with our applications of discrete calculus to the differential, this time in the context of the definite integral. Instead of using the fundamental theorem of integral calculus, we sometimes need to take a different approach, since, as you know, some integrals are hard to compute. However, even the very definition of the definite integral in terms of a limit of Riemann sums invokes the language of discrete calculus using what looks like a forward difference. Let's explore how sequences enter the picture. Let's assume that one is given a sequence of x values, x sub n, going from, say, x naught to x capital N. This is bounding our domain of integration. And then one is given a sequence f of function values, f sub n, that is thought of as a sampling of some smooth or continuous function, f. Now the question is, given only these values, how can we approximate the integral, even though we do not know the actual function f, but only the sample values? Well, of course, we can't get the exact answer, but we can approximate. The simplest approximation is the Riemann sum itself. If we consider our sequence of x values and our sequence of f values as determining the partition and the function values, then we can write out a Riemann sum of the form sum n goes from 0 to capital N minus 1 of f sub n times delta x n, that is the forward difference of x. We might call this the left Riemann sum, because if we take a partition starting with x naught and using the forward difference of our sequence x, then, of course, the sample point that we have chosen for this partition is the leftmost point. Notice that the sum is only going up to n minus 1, and we do not include that right endpoint. Now we can reverse things and use what we might call a right Riemann sum, ignoring the first sample point at x naught, and summing up all the rest using the backward difference of x. As approximations, these Riemann sums are not terribly good. On any given subinterval, you're probably going to estimate too low or too high. There's a better way to do things. Instead of using rectangles, one could use a trapezoid. This is the basis for what is called the trapezoid rule of numerical integration. What's the area of one of these trapezoidal elements? Well, of course, it's the same as taking the midpoint and evaluating the area of the rectangle defined thereby. When one works out what that means in terms of the sequence, it is the midpoint height, that is Fn, plus 1/2 delta F at n times the width, delta x at n, where here we're using the forward difference. If we sum this up over all of the intervals, let's say as n goes from 0 to capital N minus 1, then one obtains a much better estimate for the definite integral of f. A few remarks are in order. First, the trapezoid rule is really just an average of the left and the right-hand Riemann sums. Second, if you're in the context of a uniform grid, that is, the spacing between the x values is a constant, h, then the trapezoid rule takes on a very nice form. It is this width or step size, h, times the following weighted sum of the function values, f. The first point is weighted with the coefficient 1/2. The last point, f sub capital N, likewise. All of the other interior sample points have weights 1, and so one simply takes the sum. This is a very simple formula, both to remember and to use. There's an even better approximation that is called Simpson's rule. Its derivation tends to be unexplained in most calculus courses, but we're going to take the time and do it. Simpson's rule is a third-order method. That means we approximate the integrand f by a polynomial of degree 3. How do you approximate a function with a polynomial? Well, you already know the answer to that. We do a Taylor expansion. Let's set things up so that we're expanding about x equals 0 for convenience. We keep all terms of order 3 and below and pack everything else into big O of x to the 4th. We're going to focus on the range as x goes from negative h to positive h, where h is our step size. Therefore, the higher order terms can be written as big O of h to the 4th. That's going to be important later. Now, what do we want to do? We want to integrate from negative h to h, and so we can integrate each term in this Taylor expansion. Now, keeping in mind that these derivatives are all evaluated at 0, and hence constants, we see that because we're integrating over a symmetric domain, all of the odd degree terms in x integrate out to give us 0. We're left with a much simpler integral. How do we do that? Well, the first term is a constant, f evaluated at 0. That integrates to that constant times x. The second term has an x squared in it. That integrates to x cubed over 3, with the constants out in front. The error terms, big O of h to the 4th, when we're integrating from negative h to h, still gives us something that is in big O of h to the 4th. Now, when we evaluate from negative h to h, we can simply evaluate from 0 to h and pull out a constant of 2, if we like. This gives us an expression for the integral that requires knowing the function value at 0 and the second derivative of that function at 0. Now, the first term is going to be easy. If I'm given sample points, let's say at xn and xn minus 1 and xn plus 1, then evaluating at the middle point, that is at xn, is simple. That function is simply f sub n. But how do we estimate the second derivative of our integrand when all we know is the function value where we are and to the left and the right? Well, this requires remembering a few things from discrete calculus. First of all, we write the forward and the backward differences in terms of operators, the shift operator E and the identity operator I. When you don't have the ability to move 2 steps in front or behind, the proper way to estimate a second derivative is to use the second central difference. This is the forward difference of the backward difference, or the backward difference of the forward difference. It doesn't matter. In either case, what is this going to give you? Well, in language of operators, we can simply multiply things out. And we see that the second central difference of f at n is fn minus 1 minus twice fn plus fn plus 1. This is a good estimate for the second derivative. Well, not exactly. We have to be a little bit careful here. Remember, the second derivative is d squared f over dx squared. So to estimate that, we'll use the second central difference of f in the numerator, and in the denominator, we'll use delta x at n squared. Of course, that delta x is our uniform step size, h, and so we get an h squared in the denominator. Applying the second central difference, we obtain, after a little bit of algebraic simplification, an estimate for the integral from negative h to h as h times quantity 1/3 fn minus 1 plus 4/3 fn plus 1/3 fn plus 1. That is the basis of Simpson's rule. It was a lot of work, but let's see how it all comes together. We're going to assume that our integration domain is divided into equally spaced subintervals with h. We're going to set it up so that there is an even number of these subintervals so that we can apply Simpson's rule on incident pairs. On each such pair of subintervals with h, we weight the function values by these coefficients 1/3, 4/3, and 1/3 that we derived in our previous few slides. Now we do this on all pairs of incident subintervals and then add the results of these integrals together, being careful to account for what happens on the overlaps. When we do so, we obtain a system of weights for the function values, and this comprises Simpson's rule. We can approximate the integral of f as h, the width, times 1/3 f0 plus 4/3 f1 plus 2/3 f2, etc., with 2/3 and 4/3 alternating until the very end, where the last point, f capital N, has weight 1/3. Let's summarize our integration methods under the assumption of a uniform grid of step size h. In this case, all of the methods can be described in terms of the weights that are placed on the sampled function values, f sub n. In the left and the right Riemann sums, we simply ignore one of the endpoints, whereas in the trapezoid rule, we're averaging things together. Simpson's rule, as we saw, has a more complicated system of weights. Now, all of these methods have an order associated to them. We used a third order curve to approximate the integrand in Simpson's rule. The trapezoid rule is a first order method. We used line segments. The left and right Riemann sums are 0th order methods. We just took the constants and built rectangles from them. Because all of these are really using some Taylor series to approximate the integral, they all have an error term that can be expressed in terms of big O of the step size, h, and one can describe the accuracy of the method in terms of big O. Here, Simpson's rule is best, with the error term being in big O of h to the 4th. The trapezoid rule, big O of h squared. The Riemann sums, left and right, have error in big O of h. Let's put these methods to the test in the context of an example, the answer to which we already know. Consider the integral of 1 over x, as x goes from 1 to e. This is, of course, log of e minus log of 1, that is 1. If we take our domain and divide it up into 6 equally spaced subintervals, computing the sample points at each, then how do we proceed? Well, in this case, h is e minus 1 divided by 6. For the left Riemann sum, we multiply the sample values f sub n by this h, and then add them all up, not taking that last endpoint. When we do so, we get an answer that is not too bad. It's within 10% of the correct answer. If we do a right Riemann sum, then because of the convexity of this curve 1 over x, we get a very different value. It is under the true value instead of over, again by about 10%. The trapezoid rule is a great improvement over these methods, returning an answer that is within 1% of the correct answer. Notice that we're using almost exactly the same values, just balancing out what happens at the left and the right-hand endpoints. But Simpson's rule beats them all when we use that system of weights. Those third-order approximants return a value of that integral that is much better than any of the other methods we've studied. This is really just the very beginnings of the wonderful subject of numerical analysis that comprises both numerical ODEs, numerical integration, and more. If you've enjoyed these introductory lectures, you'll want to take some dedicated courses in those areas.
This concludes our brief introduction to numerical analysis. In our next lesson, we'll continue the theme of building bridges between smooth and discrete calculus by considering the digital version of an improper integral. These are familiar objects, infinite series, but you'll see them in a new light.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 50 on infinite series.
The next few lessons are at the heart of this chapter and deal with infinite series, a hopefully not too unfamiliar topic. We're going to detail specific examples and consider convergence and divergence of series in the same manner that we dealt with convergence and divergence of improper integrals.
We continue with our program of building a calculus for sequences, considering in this lesson the analog of the improper integral. These are called infinite series, something that you've seen before, but now we're going to treat them a bit more carefully. Now, how was it that we handled improper integrals? Recall, the integral from 1 to infinity of f of x dx was defined in terms of a limit, the limit as t goes to infinity, of the finite integral of f from 1 to t. So, in defining what we mean by an infinite series, that is, the sum as n goes from 1 to infinity of a sub n, we'll use the same approach. We can think of this infinite series as being something like a discretization of an improper integral. And so we can define this sum to be the limit as t goes to infinity of the sum n goes from 1 to t of a sub n. That is, the series is really the limit of the sequence of partial sums. Recall that when it comes to improper integrals, the central and subtle question is that of convergence or divergence. The same occurs with infinite series. Now, you've seen infinite series all throughout this course from the very beginning, and I have told you repeatedly don't worry too much about convergence or divergence. We'll worry about that at the end of the course. Well, it is time to push that button. It is time for all of those worries that have been inside your head to come out, and we will deal with them. We will go through the notion of convergence or divergence slowly and carefully, giving you lots of practice so that you get good at it. Let's consider some examples of series. Some are very easy to understand. If we look at 1 plus 1 over e plus 1 over e squared plus 1 over e cubed, etc., well, we recognize this as a geometric series. So not only do we know that it converges, we know exactly to what value. On the other hand, we recall that the geometric series does not always converge. For example, if we evaluate the geometric series at -1, then one could try to argue that the appropriate value is 0, or one could argue that the appropriate convergence is to 1, or even to 1/2. None of these holds. This is a divergent series because the limit of partial sums does not exist. It oscillates. Now, some series do converge, but are so subtle in how they do so, they're very difficult to evaluate. The sum from 1 to infinity of 1 over n squared does converge, as we'll be able to show soon, but it converges to a value that is very difficult to determine exactly. That value is pi squared over 6. Some series are not so easy to figure out. Consider 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. To what, if anything, does this converge? This last example is a special series that is called the harmonic series. Let's investigate this series a little bit. We'll fire up the computer and see what happens when we add, let's say, the first 10,000 terms together. We get a result that seems decidedly finite. It's about 9.79. But what happens if we, say, add another 5,000 terms to that? Well, our result is only a little bit bigger. We would guess that this is about to converge, since the next term in the series is 1 over 15,001. That is quite small. But let's just check it. Let's add the first 20,000 terms together. Well, we can see that we're slowing down a bit. We've only gone about 0.3 more, not even that. Still, I'm not going to be quite comfortable until I see that it's converged to several decimal places. But this does not appear to be happening, even with 25,000 terms. So let's sum up the first 100,000 terms. Surely, if this diverges and goes off to infinity, then we would see it. Well, the answer in this case is just a little bit more than we had before, but not so little as to make me conclude that it converges. So what is happening in this case? Well, we're going to have to use something beyond a calculator to determine convergence or divergence in this case. What we're going to use is our calculus intuition. The harmonic series reminds us of the improper integral, as x goes from 1 to infinity, of 1 over x dx. Indeed, we can consider that sum, that series, as a discretization of this integral, as a left Riemann sum of this integral with a uniform partition of step size 1. Now we know that the integral of 1 over x as x goes from 1 to infinity diverges. And we can conclude from the geometry of this diagram, if nothing else, that the harmonic series is strictly bigger. Therefore, we can conclude that the harmonic series diverges. What's wonderful about this is that we've used our continuous or smooth calculus understanding to conclude things about this discrete calculus example. This discussion raises the question, what can you trust when it comes to determining convergence or divergence? As we've seen, a calculator is not the best tool for determining convergence or divergence. What about your intuition? Maybe you should just get a feel for what works. Well, intuition is also flawed. Let's look at an example. I claim that the series 1 minus a half plus a third minus a fourth plus a fifth, etc., something that we'll call the alternating harmonic series, does converge, and it converges to a value of log of 2. Now, why is that the case? Well, recall that log of 1 plus x is exactly this kind of alternating sum of x to the n over n. If we evaluate this at x equals 1, then we obtain this value. Now, technically speaking, 1 is not in the interval of convergence for this series, but hey, trust me. You can trust me. This actually does converge. Now, if you believe that, then what happens when you multiply everything by 1/2? Well, of course, you just multiply each term by 1/2. That is definitely true. Now, if we spread those terms out a little bit and add everything together term-wise, what happens? Well, we get 1. Negative 1/2 plus 1/2 is 0. We pull down the 1/3. Negative 1/4 minus 1/4, that's a minus 1/2. Pull down the 1/5. The 1/6 cancel. Pull down the 1/7, etc. I think you can keep going with this. Some of the terms cancel. Some of the terms add together. What is this series? Well, it converges, and it converges, as it must, to 3/2 log 2. That is log 2 plus 1/2 log 2. This is true. Trust me. But at this point, we grow quite concerned, because if we rearrange the terms, we get exactly what we started with. It is a fact that by rearranging the terms in the alternating harmonic series, we obtain a different answer. That means your intuition is not so good all the time. So what can you trust? You can't even trust me. Sometimes I make mistakes. There's one thing you can trust, and that is logic. Careful, deductive reasoning. We are going to use tests for convergence or divergence that are based on logic and calculus. That is what you can trust. In general, the way that this is going to work is as follows. You'll start with some given sequence, and you want to determine whether the series converges or diverges. You'll have several, about a half a dozen or more tests to choose from. Not all tests apply to all series. So you check to see whether a given test applies. If it doesn't, choose another. If it does, then apply the test. Some tests don't work with a given series, in which case you try again. But if the test does work, then you're done. You've determined convergence or divergence. Unfortunately, you might run out of tests, in which case you fail. But that won't happen. We're going to have lots of tests. Here's the first one. This is called the nth term test. And it goes as follows. It's an if-then statement. If the hypotheses are satisfied, then the conclusion follows. Here's the hypothesis. If the limit as n goes to infinity of a sub n is not equal to 0, then the series diverges. That's it. Very, very simple. Now, in terms of applicability, this is a 4-star test. It applies to any series. No problem. It's easy to use. You just take the limit of the nth term as n goes to infinity and check whether it's 0 or not. But in terms of overall usefulness, well, this is very limited in the sense that it only tells you one thing, whether the series diverges. If that limit is equal to 0, well, you don't know anything. What do I mean by that? Let's look at some examples. If we consider the sum from 0 to infinity of 4 to the n minus 3 to the n over 4 to the n plus 2 to the n, let's check it. The limit as n goes to infinity of the nth term is, after a little bit of factoring, the limit as n goes to infinity of 1 minus 3/4 to the n over 1 minus 1/2 to the n. Well, 3/4 to the n and 1/2 to the n both get very, very close to 0. Therefore, this limit is 1, which is decidedly non-zero. Therefore, this series diverges according to the nth term test. So far, so good. What about the series? As n goes from 0 to infinity, -1 to the n over n factorial. Well, if we take the limit of a sub n as n goes to infinity, we get either plus or minus 1 in the numerator and n factorial in the denominator. That is definitely 0. And indeed, this series converges. We know that this is e to the x for x equals -1. Simple enough. But what about the harmonic series, the sum of 1 over n? Well, if we take the limit as n goes to infinity, we get the limit of 1 over n. That's equal to 0. But wait a minute, we already know that this series diverges. What is wrong? Has our test failed? No, our test has not failed. Your logic has failed. If you have a logical statement of the form, if P, then Q, then you cannot conclude if Q, then P. That is called the converse, and the converse does not always hold. In our nth term test, we have the limit as n goes to infinity of a sub n non-zero implies divergence of the series. Divergence of the series does not imply that the limit of the nth term is non-zero. The converse does not hold. What then does hold? What can be said? What can be said is the contrapositive. P implies Q is the same thing as saying that not Q implies not P. We have to negate both statements and then reverse the arrow. That contrapositive is always true. So, what we can say is that if the series converges, the negation of divergence, then the limit, the nth term, is 0. The contrapositive will hold.
So, if you follow the rules of logic, you won't get lost. Or, if you do get lost, it's because you've not followed the rules of logic. In our next 2 lessons, we'll begin introducing specific tests for measuring convergence and divergence of infinite series.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 51 on convergence tests.
This lesson will introduce a collection of tests for determining when an infinite series converges or diverges. Not all of these tests are useful in all circumstances, and it takes some time to learn which test works when. But with a little bit of practice, you'll be discerning convergence and divergence in no time.
Our goal in this lesson is to determine convergence or divergence of a series based on a sequence A sub n. We're going to employ the strategy of comparison. That is, we'll work with some other sequence, say B sub n, that is larger than or smaller than A sub n. Or, instead of another sequence, we might use a continuous function that is related to the original sequence. This is the basis of our first test, the integral test, a test which has some complicated hypotheses. First of all, the sequence A sub n must be positive and decreasing. Subsequent terms get smaller. Second, we need to take that sequence and connect the dots, turning it in to a continuous function, a of x, that is itself positive and decreasing and which agrees with the sequence at every integer point. If we have both of these, then we can compare the series, the sum of the a sub n's, with the integral, as x goes from 1 to infinity, of a of x dx. And these both have the same convergence or divergence. If one converges, so does the other. If one diverges, so does the other. Now, in terms of applicability, this test is not stellar. It has some strict hypotheses, and in terms of ease of use, this is also not the simplest test, since improper integrals can be tough. Its overall usefulness is limited, but there are several key examples where it works well. Why does this test work? Well, we've seen it in use once before when we determined that the harmonic series diverged. We compared it to the continuous integrand 1 over x. We saw, by taking a left Riemann sum, that the series was bounded below by the improper integral. If instead of a left Riemann sum, we took a right Riemann sum, then we get a bound in the other direction, that the series, or at least the tail, ignoring the first term, bounds from below the improper integral. Having this bound on both sides means that the series and the integral have the same convergence or divergence properties. If we look at a few examples, we'll see better how to apply this. Consider the absolutely fundamental series, sum from 1 to infinity, of 1 over n to the p, where p is a constant. This should remind you of the p integrals from when we did improper integrals. In fact, these are called the p series. And the right way to understand their convergence or divergence is to compare to the integral as x goes from 1 to infinity of 1 over x to the p dx. Now we know that these p integrals converge when p is strictly greater than 1 and diverge when p is less than or equal to 1. Therefore, the same holds for the p series. This is a set of examples you must memorize. A related example that is shown in the same manner is the sum of 1 over n times log of n to the pth power. If we continue this to the function 1 over x times log of x to the p, then we can integrate that with respect to dx and obtain an integral using a little u substitution to get log of x to the 1 minus p over 1 minus p. Evaluating those, we see that again, we get convergence when p is bigger than 1 and divergence when p is less than or equal to 1. Thus, the same convergence and divergence holds for the series. And in both these cases, we have a range of convergence for p where it's strictly greater than 1. Our next test is a comparison test between two sequences. The hypotheses are relatively simple. We have two sequences, a sub n and b sub n. Both are positive, and the b sub n's are bigger than the a sub n's. If this is true, then what can you say about the series? Well, if b sub n is bigger than or equal to a sub n, then the sum of the b sub n's is bigger than or equal to the sum of the a sub n's. That much is clear. But what can we say about convergence or divergence? Well, because all the terms are positive, if the larger of the two series converges, then the smaller one must converge as well. Now, the converse of this is not necessarily so, but the contrapositive is if the smaller series diverges, then so does the larger. Now, in terms of applicability, well, this one doesn't have so many hypotheses as the integral test. But in terms of ease of use and usefulness, well, it's not perfect, in part because it's easy to get these two results confused, and it's sometimes difficult to pick the appropriate b sub n or a sub n, or to know which is which. Let's see this in the context of some examples. If we look at the sum as n goes from 0 to infinity of 1 over quantity 4 plus negative 1 to the n to the n, that's 1 plus a third plus 1 over 5 squared plus 1 over 3 cubed plus 1 over 5 to the fourth, etc. That's a funny looking series, but it's not that hard to figure out because if we call these terms the a sub n's, they are definitely bounded above by a sequence b sub n given by 1 over 3 to the n. Summing that up gives us a geometric series, which definitely converges. Therefore, the A series converges as well. Now, one of the problems is no one told us which is A, which is B, and what we should use. We could have bounded the A sub n's by a P series, where P, in this case, is equal to 2. That P series converges, and so the comparison test would tell us that the original series converged as well. On the other hand, a perfectly good upper bound is given by 1 over n. However, this P series diverges, and it doesn't tell us anything about whether the A series converges or not. This is the subtlety in using the comparison test. P-series tend to be extremely helpful when using the comparison test. Consider the sum from 0 to infinity of cosine squared n over 1 plus the square root of n cubed. Let's let that be our a sub n. We can bound the numerator from above by 1, since cosine squared is always between 0 and 1. What can we do with that denominator? Well, the denominator is strictly larger than n to the 3/2. Therefore, we can bound this A sequence by a B sequence of the form 1 over n to the 3/2. Since we know something about the P series for P equals 3/2, we know that the larger series converges, therefore the smaller A series converges as well. Now let's see an example where it runs in the other direction. Consider the sum over n of 1 plus square root of n over square root of 1 plus n cubed. Now if we let that term be our a sub n, then we can bound the numerator by, let's say, 2 square root of n, and the denominator by square root of n cubed. Now that's going to give us a b sub n that is a p series with p equals 1. That is not going to help us. That series diverges. It doesn't tell us anything about the A series. So what are we going to do? Well, we implicitly assumed that our given was the A, but there's no reason why that has to be the case. Let's let this be the B terms, and we can choose an A term that bounds from below, taking a numerator of square root of n and a denominator of, let's say, 2n cubed. Then we get a lower bound for the B terms. Since the A terms give us a P series with P equals 1, the A series diverges, and thus does the B series diverge as well. Now another example leads us to some complexity. If we let a sub n be 2n cubed plus 3n minus 8 over n to the fifth minus 5n cubed minus n squared plus 2, then what are we going to choose when we try to do the comparison test? Well, we need to bound the numerator from above. Let's say 2n cubed. No, that's not going to work because we've got the 3n. Let's say 3n cubed. That will do the job. The denominator, well, we can bound from below by 2n to the fifth. No. N to the fourth. No, that's not going to be good. That gives us a harmonic series for the b sub n. That diverges. This gets very complicated. Maybe the comparison test is the wrong one. Instead, let's try an integral test. Who wants to integrate 2x cubed plus 3x minus 8 over x to the fifth minus 5x cubed minus x squared plus 2? Hello, class? Where'd everyone go? Well, what are we going to do in this case? Asymptotic analysis is going to save us, as it has done so many times before. Taking this a of x, we see that the leading order term is 2 over x squared. Everything else is in big O of 1 over x to the fourth as x goes to infinity. Well, the same thing holds for the discrete setting with our sequence a sub n. Since the leading order term is a p series with p equals 2, we know that that converges. Therefore, we know that this series converges because we know the leading order term. That's the idea behind our last test in this lesson, the limit test. The limit test says if you have two positive sequences that have the same asymptotics, the same leading order term, specifically if their limit of the quotient as n goes to infinity is some number that is strictly between 0 and infinity, then these two series have the same convergence or divergence behavior. This is a wonderful test, very easy to apply and to use, and its overall usefulness is very high as well. Let's see some examples where we compute the leading order terms, just as we did with improper integrals. Consider the sum over n of log squared of quantity 1 plus 1 over n squared. That looks very complicated to figure out. I don't want to try an integral test with that. I don't know what to compare it to, but I do know the Taylor series for log of 1 plus something, where that something is very small. I know that the leading order term for this sequence is 1 over n squared, quantity squared. That is 1 over n to the fourth. That's a p series. With p equals 4, it converges. Thus does my original series converge. Here's another crazy-looking example. We'll put a polynomial on top and something with some square roots in it down below. All we need to do is compute the leading order term. For the numerator, It's an n squared with a 3 in front, but forget about the constant. In the denominator, the leading order term is n times n to the 5/3. When you get the exponents right, you see that the leading order term is 1 over n to the 2/3. That's a p series with p equals 2/3. Psst, forget it. That diverges. And so does the original series. Lastly, consider n times pi to the n over the hyperbolic cosine of n. Well, the leading order term in hyperbolic cosine is exponential in n. Therefore, with a little bit of factoring, we see that the leading order term is n times pi over e to the n. This definitely diverges. Always look to compute the leading order term.
All of the tests that we've considered in this lesson are based on some form of comparison and ultimately reduce to finding the asymptotics, or leading order term, in the sum. Isn't it a good thing that we're familiar with asymptotics from earlier in the course? In our next lesson, we'll look at a different collection of tests, ones that are based on the geometric series.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 52 on Convergence Tests, Part 2.
One of the first series that we saw in this course was the geometric series. In this lesson, we're going to leverage our understanding of the geometric series to provide us with two additional tests for series convergence. These are the root test and the ratio test.
There is one series whose convergence and divergence we understand well. Indeed, from the very beginning of this course, we have understood the geometric series and when precisely it converges. We're going to use that as the basis for two convergence tests for more general series. The first of these tests is called the root test. It goes as follows. The hypotheses are very minimal. We just need a positive sequence, a sub n. From that, we compute the following quantity, rho, defined to be the limit as n goes to infinity of the nth root of a sub n. The test is as follows. The series sum of a sub n converges if rho is less than 1. If rho is greater than 1, then the series diverges. Now you might wonder, what happens if rho equals 1? Haha, the test fails. It says nothing in that case. Now, as far as applicability, why, this is a very general test. It applies to almost anything. Its ease of use, well, it depends. Computing the nth root and taking a limit as n goes to infinity, that can be a little difficult, and that limits the usefulness of this test. However, when it does work, it does what other tests usually cannot do. Let's see some examples. Consider the sum n goes from 1 to infinity of quantity log of 1 plus cosine 1 over n, all raised to the 1/2 n power. That looks very difficult with regards to comparisons or integral tests or anything of that sort. However, if we apply the root test, then we compute rho, the limit as n goes to infinity of the nth root of a sub n. Since a sub n involves an exponent with an n in it, this nth root cancels that, and we're left with the limit as n goes to infinity of the square root of log of quantity 1 plus cosine 1 over n. Well, we can evaluate that limit. As n goes to infinity, cosine of 1 over n is tending towards 1. Therefore, rho is equal to the square root of the log of 2. That is definitely less than 1, and that means that this series converges. Was that obvious to you from the beginning? Wasn't obvious to me. Well, here's another example. Let's look at the p series, where a sub n is 1 over n to the p for some constant p. In this case, when we compute rho, what happens? Well, we see some of the limitations of the root test. We need to compute the limit as n goes to infinity of the nth root of n, and then raise that to the minus pth power. Well, that limit of the nth root of n is equal to 1, and 1 to anything is 1. This test fails for the p series. Of course, this must be the case because depending on the value of p, the p series either converges or diverges. In this case, the root test doesn't tell you. Now, the reason why the root test works is through a comparison to the geometric series. In the geometric series, a sub n is really x to the n. And we see that in taking the nth root, if we get something that eventually behaves like a geometric series, that is, where the nth root of a sub n is tending to a number that is less than 1, then we get convergence. But there's another way that we could use the geometric series as well. What if, instead of looking at the nth root of the nth term, we looked at the limit, as n goes to infinity, of the ratio between subsequent terms? For the geometric series, a sub n plus 1 divided by a sub n is really x to the n plus 1 divided by x to the n, that is x. We expect similar types of results with this ratio. Indeed, that is the basis of the ratio test. If, as before, we have a positive sequence and we compute rho, this time to be the limit as n goes to infinity of a sub n plus 1 over a sub n, then the exact same conclusions hold. When this quantity is less than 1, the series converges. If this quantity is greater than 1, the series diverges. Now, this is a test. This test tends to be extremely easy to use and extremely useful, so much so that for most series, the ratio test should be your first choice. Let's see a few examples. Consider the sum, n goes from 0 to infinity, of n factorial cubed over quantity 3n factorial. Now, this could look a little bit confusing. Does this converge? Does it diverge? Well, let's see what the ratio test has to say. In this case, a sub n equals n factorial cubed over quantity 3n factorial. A sub n plus 1, well, we have to be careful when we're doing factorials. This is n plus 1 factorial quantity cubed over quantity 3n plus 3 factorial. Now, when we compute rho, that is the limit of the ratio, remember, it's a sub n plus 1 on top, a sub n below. We can evaluate this by multiplying a sub n plus 1 times the reciprocal of a sub n. When we do so, because of these factorials, there's a great deal of cancellation. The n plus 1 factorial cubed cancels with the n factorial cubed, leaving just an n plus 1 quantity cubed. Likewise, with the 3n factorial and the quantity 3n plus 3 factorial, we are left with the limit as n goes to infinity of n plus 1 quantity cubed over 3n plus 3 times 3n plus 2 times 3n plus 1. The leading term is cubic in n and cancels in the numerator and the denominator, yielding 1/27. That is much less than 1, and we have a convergent series. Here's another example. Consider the sum of n to the n over n factorial. You might be able to argue, based on what you know about n to the n, that this diverges. That's certainly what I would guess. But let's say we needed to show that explicitly. Well, we could try the ratio test. Let's see what we get. A sub n is n to the n over n factorial. A sub n plus 1 is n plus 1 quantity to the n plus 1 over quantity n plus 1 factorial. When we compute this limit, rho, we get n plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n. As before, there's quite a bit of cancellation going on with these factorials, and we're left with the limit as n goes to infinity of n plus 1 to the n plus 1 over n plus 1 times 1 over n to the n. There's some canceling that goes on there. And what do we get? We get, after a little bit of rewriting, a limit that we've seen before. The limit as n goes to infinity of quantity 1 plus 1 over n all to the nth. That is e. That means the ratio of the subsequent terms tends to a number that is bigger than 1. That is precisely e. That means this series diverges, as we thought. Now, sometimes it's not clear exactly which test ought to be used. Consider the following complicated-looking series. You've got odd numbers in the numerator and the product of even numbers in the denominator, and 1 over 2 to the n. What do we do? Well, let's try the ratio test. In this case, a sub n is the product of odd numbers up to 2n minus 1 divided by the product of even numbers up to 2n with an extra 1 over 2 to the n in the denominator. When we substitute in n plus 1, we have to up the index on all these terms. But notice the amount of cancellation that happens when we compute the ratio of a n plus 1 to a n. After all of that cancellation, we're really only left with just a couple of terms. That would be 2n plus 1 in the numerator and 2 times quantity 2n plus 2 in the denominator. The leading order terms in numerator and denominator are 2n and 4n, respectively. That yields a limit of 1/2. Therefore, this series converges. It converges to something very nice. You'll learn to what soon. Sometimes it's not always clear which test is going to be best. Consider the sum as n goes from 0 to infinity of pi to the 2/3 n divided by e to the n times n factorial. What is this going to be? It seems like it ought to converge. Let's see. We could try the root test. The root test tends to work when you have something with an exponent that has an n in it. Let's see what happens if we take the limit as n goes to infinity of the nth root of pi to the 2/3 n divided by e to the n times n factorial. Well, that pi term and the e term work out nicely, but we're left with pi to the 2/3 over e times the nth root of 1 over n factorial. That is maybe not so easy to do. If you want to get fancy, then we can use Stirling's formula for the asymptotics of the factorial. Well, I don't know. I'm not really in the mood for that. I'm not quite sure how to evaluate that limit. So let's try the ratio test. Instead, we take a sub n plus 1, multiply by the reciprocal of a sub n, and take the limit as n goes to infinity. Well, this one works, and it works well. We see that rho, this limit, is equal to 0. That means that not only does this series converge, but the terms in the series get small very, very quickly. Now, if we had thought about that, we would have said, well, of course, that's true. N factorial grows much, much more quickly than pi to the 2/3 n. So certainly this must converge. On the other hand, if we had been thinking from the beginning, we might have noticed that this series is actually of the form sum 1 over n factorial times something to the n. That means we're really looking at our old friend e to the x in series form, evaluated at x equals pi to the 2/3 over e. Once you start doing convergence tests, don't forget to think. Now, there are many tests that you have at your disposal. Use them. Learn which test tends to be best with which type of series. And then, like a collection of keys, keep trying until you unlock the convergence.
This concludes our principal set of tests for determining convergence and divergence of infinite series. At this point, it would be a good idea to do a lot of homework problems so that you gain an intuition for which test works when. Just like with integration, not every method is useful in all circumstances. In our next lesson, we're going to introduce a new class of infinite series and refine our notions of convergence.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 53 on absolute and conditional convergence.
Infinite series either converge or diverge, right? Well, the real situation is a bit more complicated than that. In this lesson, we'll focus attention on series that have both positive and negative terms, and we'll refine our notion of convergence into absolute and conditional.
When it comes to determining convergence or divergence, we have at our disposal a collection of tests. Sometimes those tests work well. Sometimes, well, it's not so obvious how to proceed. Consider the following 3 series, all of which look very complicated. Following the rule of doing the ratio test first is maybe not such a good idea in this particular case. But I claim that these series are easy to figure out. The first 2 converge, the last diverges. Why is it so easy? It is easy because of this term in front, the -1 to the n, a term which, ironically, renders most of our prior tests useless. However, these are examples of alternating series, series whose terms alternate between positive and negative. Such series are very easy to work with. One often writes them in the form sum over n of -1 to the n, a sub n, where the a sub n terms are positive. Let's do one last test, the alternating series test. It begins as follows. If we have a decreasing positive sequence A sub n. Then we're going to look at the limit of these terms, just as in the nth term test. The alternating series, sum over n, -1 to the n, a sub n, converges if and only if the limit is 0, and it diverges if and only if the limit is non-zero. This is in contradistinction to the nth term test, which was not if and only if. Now, the bad part of this test is it's not very applicable. You must have an alternating series with decreasing terms. However, this test is as easy as can be, and because of the ubiquity of alternating series, it's really quite useful. How can it be that we get such a strong result for this test? Well, let us consider the convergence of an alternating series. Of course, we will look at the sequence of partial sums. That is, the sum as n goes from 0 to some t, -1 to the n, a sub n. What does the convergence of this sequence look like? Well, if it is an alternating series, then that means we start at a0, we jump backwards by the amount a1, then we jump forwards by the amount a2, backwards by the amount a3, etc. If, as per our hypotheses, the sequence of a sub n's is decreasing, that means our jumps get smaller and smaller. This means in the limit, there are only two possibilities. If the limit of the a sub n's is 0, then our jump size decreases to 0, and our series converges. If the limit of the a sub n's is non-zero, then we oscillate back and forth by that limiting jump amount. As per the nth term test, the series does not converge. Let's see how this test works in the context of the three series with which we began our lecture. All three of these are alternating series, and hence the alternating series test applies. The first is the sum of -1 to the n, pi to the n, log n squared plus 1 over n factorial times hyperbolic cosine of n to the 5/3. Now, looking at this, it's pretty obvious that the n factorial term dominates all others. Hence, the limit of the a sub n's is 0, and this series converges. No other work necessary. Likewise, in the second series, the sum of -1 to the n of 1 over log of log cubed of log to the 5th of n. This one also has terms that are going to 0, obviously. Hence, it converges without further work. The last example, involving the cube root of n to the 5th minus 3n cubed plus 2 over the square root of n cubed plus 9n squared plus 1. Well, that's not half so complicated as it looks. We could have easily computed the leading order terms of both of these and discerned through the nth term test that this diverges. This is true whether or not it's an alternating series. In all these cases, it's pretty simple. The contemplation of alternating series leads us to new definitions involving general series. We say that a series is absolutely convergent if not only does the sum of the a sub n's converge, but the sum of the absolute values of the a sub n terms also converges. We say that a series is conditionally convergent if it is a convergent series. That is, the sum of the a sub n's converges, but the sum of the absolute values of the a sub n's diverges. Of course, A series that only has positive terms in it can't be conditionally convergent. A conditionally convergent series is one that has enough negative terms, or maybe alternating terms, so as to force a weaker sort of convergence. Both of these are in distinction to a divergent series, which does not converge at all. With these definitions, there are exactly three possibilities for a series. If you're given the sequence, then the series, the sum of the a sub n's, might diverge. If it converges, one checks the convergence of the absolute values. If that does not converge, then you have a conditionally convergent series. Otherwise, you have an absolutely convergent series. These three are mutually exclusive. Every series is one of these three types and only one. Let's see some examples. If we take the sum from 1 to infinity of -1 to the n plus 1 times 1 over n squared, this is 1 minus a fourth plus a ninth minus 1/16, etc. What can we say about this? Well, it definitely converges based on the alternating series test. When we take the absolute values, what do we get? We get a p-series with p equals 2. That also converges. Therefore, this is an example of an absolutely convergent series. On the other hand, if we take what we might call the alternating harmonic series, -1 to the n plus 1 over n, then by the alternating series test, this does converge. However, when we take the absolute values of the terms, we get the harmonic series, which diverges. Therefore, this is the canonical example of a conditionally convergent series. If we take the sum of -1 to the n, well, we've already seen that that is a divergent series, and taking away the negative signs is not going to change that, not at all. In general, if we look at an alternating p-series, where we take 1 over n to the p and have the signs alternate on it, then instead of having convergence at p bigger than 1 and divergence for p less than or equal to 1, in this alternating scenario, we have absolute convergence for p strictly bigger than 1 and conditional convergence for p less than or equal to 1. For the remainder of this course, we're going to go back and reconsider all of the convergences that we have seen or implied and revisit them in light of our new definitions. Recall from the very beginning of this class how we showed that log of 1 plus x is the alternating sum of x to the n over n. Now you remember, and I remember, that this only works when x is strictly less than 1 in absolute value, just like the geometric series. However, I claim that we could bend the rules just a little bit. What happens when we substitute x equals 1 into this formula? We seem to get that log of 2 is 1 minus a half plus a third minus a fourth plus a fifth, etc. Is this true? In the past, I've asked you to trust me, but now you don't need me because you have enough tools at your disposal. The series on the right does converge by the alternating series test. However, since it is an alternating harmonic series, its convergence is conditional. it limits to the value on the left, log of 2. Now recall that this series is a little bit tricky. We have argued in the past that by rearranging the terms and combining in the appropriate manner, we seem to get something that is a different value, namely 3/2 log 2, simply by rearranging the terms in the original series that was presented as a mystery. Here, it is presented as a warning. The real reason for that strange behavior comes from the conditional convergence of the series. Whenever you have a conditionally convergent series, you should be cautious. It is a dangerous situation. You are so close to having a divergent series. You've got to be careful. On the other hand, when you have an absolutely convergent series, you're in great shape. It is a theorem that you can rearrange the terms in an absolutely convergent series at will, as you wish, and the sum remains constant. Absolutely convergent series are very robust and will be very helpful when you're working with Taylor series. On the other hand, this is not the case for conditionally convergent series. It is a result whose proof will not fit in this margin that, given a conditionally convergent series, you can rearrange the terms to sum up to any number you wish. They are a bit dangerous. Beware of them, but trust in absolute convergence.
The distinction between absolute and conditional convergence may seem a little academic. After all, what does it matter to applications in the sciences? It makes a big difference, as we'll see in our next 2 lessons, which will take us back to the very beginnings of this course.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 54 on Power Series.
At last, we've assembled all the tools we need to adequately and accurately describe how, when, and in what manner infinite series converge. In this lesson, we're going to apply these tools to power series.
In this chapter, and indeed in this course, we've seen several instances of turning functions into sequences through some sampling process. We now turn to the problem of reversing that machine, of converting sequences into functions. One mechanism for doing so is the power series. A power series in X is simply a series that has the variable x inside of it as a monomial term, something of the form sum n goes from 0 to infinity of a sub n, x to the n, where now a sub n is considered a coefficient. We're going to think of the notion of a power series as a machine or an operator that converts a sequence, a sub n, into a function, f of x. Let's begin with some simple examples. If we have a sequence, all of whose terms are 0, except for 1 in the nth slot, then the power series is simply the monomial x to the n. Now, if we have a finite sequence in the sense that only finitely many of the terms are non-zero, then this will have a power series that is a sum of monomials with coefficients in front of them that eventually terminates. We call that a polynomial. Now, if we have something that does not eventually end in zeros, we're going to have to be a bit more careful, but this isn't so mysterious. If we have the sequence of all ones, we recognize that the power series for that sequence is simply the geometric series. And this gives us the function 1 over 1 minus x, at least when x is less than 1 in absolute value. Other sequences can be easily seen to correspond to interesting functions, though one may have to do a bit of algebra to see it. If we look at certain sequences, we'll recognize some old friends, log of 1 plus x, or e to the x. These correspond to certain power series. Now, what if we have a sequence that does not go to 0, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc.? Will that converge to anything? Well, of course, this isn't so bad. This one corresponds to the function 1 over quantity 1 plus x squared, as you can see from squaring the geometric series. In fact, we can have sequences that grow rather large, but which have power series that converge to something very simple. Now, what if we just take any old interesting sequence of coefficients? What will that converge to? Sometimes it's a bit of a mystery. Let's look at the Fibonacci sequence and let us denote by script f the power series whose coefficients are f sub n, the terms in the Fibonacci sequence. Now, if we were to multiply this power series by x, what would happen? It would give us a new power series associated to a shift, a right shift of the Fibonacci sequence. If we were to do it again, then we would shift over to the right yet once more. And the reason for doing this is to line up the coefficients to match the recursion relation that the Fibonacci sequence satisfies. Fn plus 2 equals Fn plus 1 plus Fn. Now, if we take a look at the coefficients in front of the monomial term x to the n for these three power series that we have written down, then we see from the recursion relation the relationship between them. The first is the sum of the latter two. And so if we were to subtract x times script f and x squared times script f from script f, what would we obtain? Most of the coefficients of the monomial terms are 0 because of the recursion relation. When we add up these power series, the only thing that is non-zero is in the constant term, where we get f naught, and the first order term, where we get f1x minus f naught x. Now, because we know the exact values of f naught and f1, we see that on the left we have f minus xf minus x squared f. On the right we have simply x. Solving for script f gives us the power series formula that script f, the power series, the Fibonacci sequence, is equal to x over 1 minus x squared. Now, that's what it is, but what does it mean? What do we do with this? These functions that generate the power series have within them all sorts of interesting questions. They tie together recursive properties, enumerative properties, approximation properties, and convergence. We're going to focus on issues of convergence. Consider a power series f of x, the sum of a sub n, x to the n. The following theorem holds. For some, capital R, between 0 and infinity, perhaps achieving either of those values, f of x has the following convergence behavior. It converges absolutely. If x is less than r in absolute value, it diverges if x is bigger than r in absolute value. Now this r is a very special number associated to the power series. It's called the radius of convergence. Let's see, how would we prove this theorem? What tool would we turn to determine convergence? Well, let's start with our friend, the ratio test. Here, what we need to do is compute rho, the limit as n goes to infinity, of the ratio of the n plus first term to the nth term. Now, what are the terms? Well, here they are a sub n times x to the n. So taking the ratio of incident terms will tell us what we need. Now we have to be careful to take the absolute values, since the ratio test requires a positive sequence. Okay, so doing that, what do we see? We get some cancellation with the x's, and we can rewrite this as the limit as n goes to infinity of the absolute value of a sub n plus 1 over the absolute value of a sub n times the absolute value of x. Now, if that is less than 1, we have absolute convergence. If that is bigger than 1, we have divergence. So, where is this capital R coming from? Well, it is precisely the reciprocal of this limiting coefficient, since if we divide by this on both sides, we get the appropriate answer. When rho is less than 1, that's the same thing as saying that x is strictly less than r in absolute value. That means we have absolute convergence. When rho is bigger than 1, that's the same thing as saying x is greater than r in absolute value, and that means divergence. So what matters is this radius of convergence, capital R, the limit as n goes to infinity of absolute a sub n over a sub n plus 1. Be sure to remember that, and be sure to remember that it's the nth term over the n plus first term, not the other way. Now, this radius of convergence is called a radius of convergence because it's telling you the distance away from 0, past which your power series is going to diverge. But within that, you're fine. Now, you do have to be careful. We've said nothing about the endpoints of the domain because, of course, the ratio test tells us nothing in that case. So you're going to have to be careful and check explicitly at those endpoints. Let's see a simple example. If we consider f of x, the sum over n, negative 1 to the n, square root of n, quantity 2x to the n, then our coefficient, a sub n, is negative 1 to the n, square root of n, 2 to the n. To compute the radius of convergence, we take the limit of the a sub n divided by a sub n plus 1, all in absolute value. That gives us the limit as n goes to infinity of square root of n, 2 to the n, over square root of n plus 1, 2 to the n plus 1. That is, as you can easily see, 1/2. Therefore, within 1/2 of 0, we have absolute convergence. Outside of that, we have divergence. What happens at the endpoints? Well, we need to check what happens at x equals negative 1/2. If we plug in a value of negative 1/2 in for x, what do we get? We get the sum over n of square root of n, since the negative 1 to the n's cancel. That is a divergent series. So at the left-hand endpoint, we have divergence. At the right-hand endpoint, at x equals 1/2, you can easily see that we get the same sort of series. That, too, is going to diverge by the nth term test. Now, other series that we've seen throughout this course have similar behavior. If we look at the geometric series, this is the power series where all the coefficients are equal to 1. The radius of convergence, in this case, equals 1. And this diverges at both endpoints at plus and minus 1. If, on the other hand, we consider the power series with coefficient 1 over n, as n goes from 1 to infinity, then what do we see? This, too, has a radius of convergence equal to 1. And at the right-hand endpoint, we obtain the harmonic series, which certainly diverges. But at the left-hand endpoint, at x equals -1, we get the alternating harmonic series. That converges, but it does so conditionally, not absolutely. If we consider the power series x to the n over n squared, where the coefficient is 1 over n squared, this also has radius of convergence equal to 1, but it converges at both endpoints and does so, therefore, absolutely. Some power series come to us in a slightly different form, that of a shifted power series, something of the form sum over n of a sub n times quantity x minus c to the nth. This, of course, is just a power series shifted over by c units. In this case, if we compute the exact same radius of convergence, then what we will find is that this shifted power series converges when x minus c is less than r in absolute value. That is, when x is within r of c. R is thus a distance to the center, c, of the shifted power series. For an example of a shifted power series, consider the sum of 3x minus 2 to the n over n times 4 to the n. Now this is not in the form of x minus c to the n, so we're going to have to do a little bit of algebra to get it into that form. But I claim that by factoring out a 3/4 to the n and absorbing that 3 to the n term from the denominator into the numerator, we get the equivalent sum of 1 over n times 3/4 to the n times x minus 2/3 to the n. That means that this shifted power series is centered at x equals 2/3. Now, to determine the radius of convergence, we isolate the coefficient a sub n as 1 over n times 3/4 to the n. We compute the radius, r, as the limit as n goes to infinity of a sub n over a sub n plus 1. That yields, after some algebra, the limit of n plus 1 over n times 4/3, which is precisely 4/3. Therefore, the domain of absolute convergence is all x within 4/3 of 2/3 the center. Now, what happens at the boundary points? Well, on the left, we have x equals -2/3. That is 2/3 minus 4/3. Substituting in x equals -2/3, we obtain, after a little bit of cancellation, the alternating harmonic series. That, of course, converges. When we substitute in the right-hand endpoint, that is, x equals 2/3 plus 4/3, or 2, then we obtain, substituting in, a series which is the harmonic series. This, of course, diverges, so that we have conditional convergence on the left, divergence on the right.
In our next lesson, we're going to focus attention on a particular type of power series obtained from a smooth function f of x. Perhaps you've heard of these. They're called Taylor series.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 55 on Taylor series redux.
Like Odysseus, after his long wanderings, we finally come back home to where we began, with Taylor series. Having seen a lot of strange sights along the way, we come back wiser, with more experience. All the better for handling whatever challenges we might face here at the end.
In our last lesson, we explored power series, that is, series of the form sum over n of a sub n, x to the n. And we considered this as an operation for turning a sequence into a function, f of x. Now, the question arises, can one invert this procedure and go from the function to the sequence? Well, of course, you already know the answer to this. It is yes. We've been doing this all semester. The answer is, of course, Taylor series. Taylor expansion is really a means of turning a function into a sequence of coefficients, which, when reconstituted into a power series, gives you the original function back. In Taylor expansion about, say, x equals 0, we know that these coefficients are the nth derivatives of f at 0 divided by n factorial. But now we can return to the issue of convergence of Taylor series. Recall that at the beginning of this course, I said, don't worry about convergence too much. Just learn how to use Taylor series, and we'll get to issues of convergence later. Well, it is now later, and it's now time to worry about convergence of Taylor series. But now we can say something definite. The following theorem is crucial. If we have a power series of the form a sub n, x to the n, and we call that f of x, perhaps this is a Taylor expansion about 0, then f converges absolutely for values of x that are within r of 0, where r is the radius of convergence, the limit as n goes to infinity of a sub n over a sub n plus 1 in absolute value. Now, if this were a Taylor expansion about 0, we see that what really matters is how quickly the derivatives at 0 grow and get large. The ratio of subsequent derivatives controls the convergence radius. Now, more importantly, when you're on this interval of convergence from negative r to r, then not only does your function converge, but it's differentiable. And the derivative is what you obtain differentiating the series term by term. Moreover, f is integrable, and the integral within this domain of convergence is exactly what you would get if you integrate the series term by term. Oh, as long as you don't forget the constant. Now, what's so important about a result like this? Well, it tells us exactly what the convergence domain is and allows us to manipulate the series. Let's see how that's useful. We have claimed in the past what the Taylor series for arctan looks like. Knowing the derivative of arctan, we can express it as the integral of dx over 1 plus x squared. Using the geometric series, we can see that within that domain of absolute convergence, what do we have? The arctan is really the integral of the sum over n of quantity negative x squared to the n. Now, if we expand that out and then integrate term by term, then we get the arctan as the sum. N goes from 0 to infinity of negative 1 to the n over 2n plus 1 times x to the 2n plus 1. There's a constant of integration, but that's equal to 0, since arctan of 0 is 0. Therefore, we have our familiar series for arctan of x minus x cubed over 3, plus x to the 5th over 5, etc. That works within the domain of convergence, from negative 1 to 1, based on the geometric series. Now, what happens at the endpoints? Well, when x equals -1, then it would seem to suggest that you get pi/4 as this alternating sum, 1 minus a third plus 1/5 minus 1/7. Does that actually converge? Well, yes, it does by the alternating series test. However, this convergence is conditional right at the boundary. There's really no end to what one can do with this result. Let's begin with the geometric series and differentiate it term by term. When we do so, we obtain the sum over n of n times x to the n minus 1 equals 1 over 1 minus x quantity squared. Now let's multiply through by x on both sides. That takes us back to a simpler looking power series, that of the sum n x to the n. We see that that equals x over 1 minus x quantity squared. Now, if we evaluate this at a particular x, let's say x equals 1/10, what do we get? We get that this sum, 1/10 plus 2 100ths plus 3 1,000ths, etc., is really equal to the right-hand side evaluated at 1/10, that is 10 over 81. This has an interesting sort of decimal expansion. It's somewhat surprising that this discrete integral has such a simple answer. But of course we could keep going. We could differentiate once more and then multiply through again by x, obtaining the result n squared x to the n summed over n yields x times 1 plus x over 1 minus x cubed. If we again evaluate this at 1/10, then we get the not very intuitive answer that 1/10 plus 4 100ths plus 9 1,000ths, etc. equals 110 divided by 729. Such results are very easy to obtain. You will undoubtedly recall that Taylor series can be useful in defining new functions. Consider the Fresnel integrals. C of x equal to the integral of cosine t squared as t goes from 0 to x, and a complementary Fresnel integral, s of x, that is the same, but with sine instead of cosine. These functions are very useful in optics and diffraction, but it's not so easy to come up with an antiderivative for sine or cosine of t squared. That's why these functions have special names. Now you could try to graph these functions. You would notice that they're oscillatory, as is expected from their form. But how do you really get your hands on them? Well, one way to do so would be to use a Taylor series. Expand out cosine t squared or sine t squared using the familiar formulae, and then integrating term by term, substituting in the values from 0 to x gives us power series formulae for these functions that are extremely useful, especially for smaller values of x. We know enough now to answer the question of when a Taylor series converges, but there's one question we have not answered. How do we know that what the Taylor series converges to is actually the function you began with? Let's say that we've expanded f of x about x equals a. Then, how do we know that that Taylor expansion converges to f? Well, it certainly must be the case that f is smooth. That is, all of the derivatives at a exist. Secondly, x must be within the domain of convergence. That is, within R of a. Very good, but even with both of those conditions satisfied, it's not enough. In fact, we make the definition that f is a real analytic function at a if, for all values of x close to a, the Taylor series exists and converges to f of x. Now, why would we need such a definition? Some functions are not real analytic. Consider the following example. Let f of x be defined as e to the minus 1 over x for x strictly positive and 0 otherwise. Now, your first clue that something is funny is if we write out the series definition for e to the negative 1 over x, we don't get a power series. We get a power series in 1 over x. That's going to give us problems when x is near 0, so there's no way that we're going to be able to compute the derivatives of this function by looking at the coefficients of the series. So let's do it the old-fashioned way. Let's compute the derivative of f at 0 by taking the limit as h goes to 0 of f of h minus f of 0 over h. If we do this limit from the right, then we can evaluate f of h as e to the minus 1 over h. Now, f of 0 is, of course, 0, and so we're left with the limit as h goes to 0 from the right of e to the negative 1 over h divided by h. If we change variables and let t be 1 over h, then this is the same thing as the limit as t goes to infinity of t times e to the minus t. Now that we know because exponential beats polynomial. This is 0. So I claim that with a little bit more work using a similar approach, you can show that all of the derivatives of f at 0 are exactly 0. That means that if you take the Taylor expansion of this function, it exists, and it is precisely 0. Every single coefficient in the Taylor series is 0. However, the function itself is positive for values of x that are strictly bigger than 0. This is a smooth function, but it is not real analytic. This leads us to an image of the universe of functions, beginning with the simplest functions. At the very core of this universe lie the polynomials. These are themselves divided or graded into different realms, beginning with the constants, and then the first-order polynomials, the quadratics, the cubics, etc., each filling out, degree by degree, larger and larger subspaces of simple functions. But this is not all there is, since polynomials have power series that eventually terminate. Beyond the space of polynomials lie those functions whose Taylor series exist and converge to the functions, that is, the real analytic functions, like e to the x, sine of x, cosine of x, all those beautiful functions we've been working with all term. However, beyond these still lie other functions, more mysterious functions, for which Taylor expansion is not sufficient to describe them. One normally doesn't run into such things. That's why we haven't focused too much attention on them, but you should know that they lie out beyond the real analytics. This leads us to our last image of what Taylor expansion really is. Taylor expansion can be thought of as projection to the space of polynomials, where computing a Taylor polynomial is a projection to one of these finite subspaces. Throwing away the higher order terms really is a form of projection.
My hope is that you now have a deeper understanding of what Taylor series are, where they converge, and how they're situated in the space of all functions. In our next lesson, we're going to descend from these ethereal heights to tackle a more earthly problem, that of approximation and error.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 56 on approximation and error.
We've seen the big picture of how Taylor series and polynomial approximations to functions work. In this lesson, we're going to change focus and detail exactly what happens when we perform approximations.
By now, you know that the sum of 1 over n squared converges, since it is a p-series with p equal to 2. But to what does it converge? We've claimed in the past that this converges to pi squared over 6. That is a deep result. We can't get that easily, so let's approximate. The true value of pi squared over 6 is, in decimal form, 1.6449, etc. How many terms would we have to sum up in this series to get within a certain amount of that true value? Well, let's fire up the computer and see what happens if we add up, let's say, the first 10 terms. Then we get an answer that is, well, it's within a neighborhood. It's not exactly really close. So let's add up the first 20 terms and see how close we get. Now we're doing a fair bit better. If we take a little bit more time and effort, compute the first 100 terms, then it seems as though we're definitely within 1% of the true answer. And if we added up the first 1,000 terms, well, now we're getting something that is really fairly close to pi squared over 6. But how close? Well, in general, you're never going to be able to get to the truth. The true answer involves a limit, and that just takes a lot of work. In general, what you can do is come up with an approximation, let's say by summing up terms up to and including a sub capital N. Now what's left over is the error that will denote E sub capital N. You're not going to be able to compute that error exactly, since then you would know the truth, but you can control or bound that error. Let's see how that works in the context of an alternating series. Let's consider a series that satisfies the criteria of the alternating series test. That is, the sum of -1 to the n, a sub n, where the a sub n's are positive, decreasing, and limiting to 0. Then remember how this convergence happens. As you take the partial sums, you're always jumping over the true answer to the right and then back to the left because of the alternating nature. Then, in this case, it's easy to get an upper bound on the error, E sub n, in absolute value. It is precisely a sub n plus 1, the next term in this series, because you're always overshooting. When you have an alternating series, this result is simple and useful. Let's consider the approximation of 1 over square root of e, with the goal of getting within 1/1000th. Well, if we use our familiar expansion for e to the x, where x equals -1/2, then we see this is really an alternating series, with the a sub n term being equal to 1 over n factorial times 2 to the n. Now, if our goal is to add up a finite number of these terms and get the error less than 1/1000th, then the alternating series bound says that we need to find a capital N so that a sub capital N plus 1 is less than 1/1000th. Well, what is a sub capital N plus 1? It is capital N plus 1 quantity factorial times 2 to the capital N plus 1. Getting that less than 1/1000th is not so hard. That's going to work whenever n plus 1 factorial times 2 to the n plus 1 is greater than 1000. That's true whenever n is bigger than or equal to 4. So it doesn't take many terms to approximate 1 over square root of e. But let's consider what it would take to approximate log of 2 using the alternating harmonic series. In this case, a sub n is 1 over n. In order to get the error less than 1/1000th, what do we need? Well, again, by the alternating series bound, we need a sub capital N plus 1 less than 1/1000th. That's the same thing as saying n is greater than or equal to 1000. And that is a lot of terms to get within the same error amount as we used for an exponential. What happens if you don't have an alternating series? Well, you need a different error bound. There is one associated to the integral test. Let's say that you have continued your series a sub n to a function a of x and have shown convergence by means of integrating this function. Then one can see that the tail, the e sub n term, has a natural lower bound in terms of the integral of a of x. Specifically, if one integrates as x goes from n plus 1 to infinity, then that is a strict lower bound for e sub n. Now that's not optimal. We tend to want an upper bound for the error. But note what we can do. If we slide everything over by 1 unit, then the appropriate upper bound for the error is the integral of a of x dx as x goes from n to infinity. This is remarkable in that we get a bound in both directions. With this in mind, let's see what it would take to get close to pi squared over 6 when we sum up terms of the form 1 over n squared. Now we know the value of pi squared over 6, and let's say that we want to get within 1/1000th. Well, we know that this p-series converges by the integral test using a continuous function, a of x equals 1 over x squared. By the integral test bound, e sub capital N is less than the integral from capital N to infinity of this a sub x. We've done the integral of 1 over x squared enough times so that you'll believe me when I say that this integral comes to 1 over capital N. Now, if we want that to be less than 1/1000th, that's really saying that n has to be larger than 1,000. And if you'll recall when we did some of our computations, that is exactly what we saw when we summed up the first 1,000 terms. The integral test gives very precise bounds. If you don't have an integral test and you don't have an alternating series, what can you do? Well, there's one last error bound that involves only Taylor expansion, but we're going to pay for that generality in terms of complexity, for the following result is deep and difficult to grasp. For that reason, we'll keep it simple by looking at what happens at f of x for x close to 0. Assume that f is smooth, then Taylor expand f about x equals 0, keeping only terms up to and including order n. Now, of course, f is not equal to this Taylor polynomial. It's just an approximation, so there's some error. But here, the error term, e sub n, is a function of x and not a constant. So what can we say about that error function? Well, the first thing that we can say is that e sub n of x is in big O of x to the n plus 1. That's not too surprising. Everything else is higher order terms. On the other hand, this is kind of a weak result in that in big O, you're only finding out what happens up to a constant, and in the limit as x goes to 0. What we'd really like is a more explicit bound that we can use to get numerical results. Well, there is a strong form of this theorem that says that the error is bounded in absolute value by some constant, c, times x to the n plus 1 over n plus 1 factorial, where this constant c serves as an upper bound to the n plus first derivative of f at all values of t between 0 and x inclusive. This is a much stronger version of the error bound and tells you that it's really the n plus first term in the Taylor expansion that is giving you control over the error. In fact, if you want to get really strong, we can replace that constant big C by exactly the n plus first derivative of f at some t that is between 0 and x. And this is a very remarkable result in that you're not bounding the error. You're saying exactly what the error equals as a function of x. What I'm not telling you is what t you have to choose in order to evaluate that n plus first derivative. Now, I'll let you work out what this would be if you replace 0 with a. Let's see how this bound works in an example. Let's approximate the square root of e within 10 to the negative 10, using the familiar expansion for e to the x and evaluating at x equals 1/2. Then what do we get? We have some e sub n, where, by the Taylor theorem, e sub n is less than some constant c over n plus 1 factorial times x to the n plus 1, in this case, x equals 1/2. And c is some constant that bounds the n plus first derivative of e to the x for all values of x between 0 and 1/2. Now, fortunately, derivatives of e to the x are easy to compute. That's just e to the x. So what is a good upper bound for e to the x? Well, since e to the x is increasing, then a good upper bound would be the right-hand endpoint, e to the 1/2. Well, that number is maybe not so easy to work with. So let's just say 2, because I know that 2 is a reasonable upper bound for e to the 1/2. Therefore, we get that e sub n is less than 1 over n plus 1 factorial times 2 to the n. That's maybe not the best bound we could come up with, but it will get the job done, because if we tally up n plus 1 factorial times 2 to the n for various values of n, we see, without too much effort, that having n bigger than or equal to 10 will work. Well, that went so well. Let's do it again, this time to estimate arcsine of 1/10 within 10 to the negative 10. Now, I won't go through the details of the Taylor expansion for arcsine of x. The terms are a little bit complicated, but not too bad if you assume that they're given. What matters is the Taylor error bound, that e sub n is less than a constant c over n plus 1 factorial times x to the n plus 1, where x equals 1/10. Now, this constant c is the critical piece of information. It's an upper bound for the n plus first derivative of arcsine of x for all x between 0 and 1/10. Now, who remembers the formula for the n plus first derivative of arcsine of x? Anybody? I don't remember it either, and this is the difficult part of using the Taylor bound. You don't necessarily know a good bound for the n plus first derivative. How are we going to solve this? Well, if the Taylor theorem is not going to work, and it's not an alternating series, and I don't think I want to integrate this function, then what do we do? Well, we're just going to have to think. But if we think, well, this is not so bad. Look at the terms in this series. We have a 1/10 and then something times 1/10 cubed, plus something times 1/10 to the 5th, etc. It seems as though every step where we go from n to n plus 2, we're picking up an extra 1/10 squared. Okay, so that's 1 over 100. But if we look at the coefficients, the 2n plus 1, and the products of odds over the products of evens, then we're picking up another factor of 10 in the denominator. And I claim that an plus 2, the next term in the series, is less than the previous term, a sub n, divided by 1,000. What this means, really, is that you're picking up 3 decimal places of accuracy with each subsequent term. And that means that if we want to get within 10 to the negative 10th, it's going to suffice to choose n bigger than or equal to 7. So the first 4 terms that we have represented on this slide suffice to approximate arcsine of 1/10 within 10 to the negative 10. Never forget to think, even if a Taylor bound doesn't work. In general, bounding errors is just hard. There's no getting around it. If you're fortunate enough to have an alternating series, then it's not so bad. If you've got something that works with an integral test, you're great. If not, you're either going to have to resort to the Taylor theorem or use your head.
That brings to a close all of the main topics of this course. We're not quite done, though. We still have a few things to say to wrap up this chapter, this course, to give you the big picture and to point ahead to some of the broader ideas you may encounter in calculus and in the world of mathematics.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 56, Bonus Material. In our main lesson, we saw, among other things, the Taylor remainder theorem that tells you an explicit bound on the error term for a Taylor expansion of f. We're looking at the version for f Taylor expanded about x equals a. The weak version, as you will recall, states that the error, e sub n, is a function that is in big O of x minus a to the n plus 1. The strong version of the theorem says that e sub n of x is exactly the n plus first derivative of f, evaluated at some t between a and x, divided by n plus 1 factorial times x minus a to the n plus first. There's no doubt that this is a difficult theorem, both to prove but even to understand. Therefore, let's consider the simplest possible case, where n is equal to 0. In this case, what we're really saying is that f of x is the 0th order approximation, f at a, plus some error term, e sub 0 of x, where this error is precisely the first derivative of f, evaluated at some t, divided by 1 factorial times x minus a to the first power. Now, we don't know exactly what the t is, but for some t, this holds. And we have that f of x equals f at a plus f prime at t times x minus a. Now, this may look familiar to you. You may recall a result that expresses this exactly. This is the mean value theorem, though perhaps you're used to seeing it in a slightly different form, with the terms rearranged and with a slightly different interpretation. Recall, the classical mean value theorem is interpreted as follows. You have a smooth function f, and you consider points a and x. In this case, look at the secant line that connects these two values on the graph of f, and consider the slope of that secant line, that is, f of x minus f of a divided by x minus a. Then there exists some value of t between a and x, at which the tangent line to the graph has slope, f prime at t, that is equal to the slope of this secant line. That classical theorem is really just a simple corollary of the Taylor remainder theorem. Let's turn to the problem of answering why this theorem holds. Now, we can't give a complete proof, but we can give the idea of at least the weak version of this theorem. Let's begin with the simplest case where n equals 0. We Taylor expand f of x about a and obtain f of x equals f at a plus the error or remainder, e of x. Now, how are we going to get a good expression for this? Well, we need a big result. The biggest result that we have at our disposal is the fundamental theorem of integral calculus. So let's feed this problem into that theorem and see what it says. The fundamental theorem tells us exactly what e of x is. It is the integral as t goes from a to x of the derivative of f prime of t, dt. Now, this seems like a tautology. According to the fundamental theorem, that integral equals f evaluated from a to x, that is, f of x minus f of a. So, of course, it works. But why is this not redundant? It's not redundant because we can start estimating this integral. For example, we can observe that this integral is in big O of x minus a as x is approaching a, or as x minus a approaches 0. But that's not all, because next we can induct and apply recursion. We know that f is a smooth function and all of its derivatives are smooth. Therefore, let's take what we know about f and apply it to f prime. I'm going to write f prime of t as f prime at a plus some error, some term that is in big O of t minus a. And now I'm going to feed that expression into the integral estimating e. E of x is the integral as t goes from a to x of f prime at a plus something in big O of t minus a. What happens when I integrate that with respect to t? Well, f prime at a is a constant, and so when I integrate that, I get f prime at a times t evaluated as t goes from a to x. That means f prime at a times quantity x minus a. What happens when I integrate something in big O of t minus a? I get something of the form, say, 1/2 quantity t minus a squared. The 1/2 doesn't matter because we're doing big O, and I take that t minus a quantity squared and evaluate as t goes from a to x. That's giving me something in big O of x minus a quantity squared. Okay, so you can see we've got the next term in the Taylor expansion by feeding our estimate of the derivative into the integral and integrating. So what are we going to do now that we have the first order expansion? Well, you guessed it, we're going to recurse or induct and apply this result to f prime of t again. F prime of t is f prime of a plus f double prime at a times t minus a plus something in big O of t minus a quantity squared. And now, as you could guess, we're going to feed that into the integral that estimates e of x. E of x is the integral as t goes from a to x of f prime at a plus f double prime at a times t minus a plus something in big O of t minus a quantity squared. What happens when we integrate this? Well, just as before, integrating f prime at a gives f prime at a times t evaluated from a to x. Now, with the next term, what happens? We have f double prime at a. That's a constant. It comes out. When we integrate t minus a, we get 1/2 t minus a quantity squared, evaluated from a to x, gives 1/2 f double prime at a times x minus a quantity squared. What happens when we integrate the next term, the big O of t minus a squared? Well, we get something of the form big O x minus a quantity cubed. And now we see that we've obtained the second order term in the Taylor expansion, and we know that the remainder to that is in big O of x minus a quantity cubed. I think this is enough for you to see the pattern of how this works. Now, of course, this is not a full proof of the Taylor remainder theorem. We have not said anything about this precise value of t, which gives you the exact error. I encourage you to, if you're curious, dig a little bit deeper and look up some more complete proofs of the Taylor remainder theorem. Some of them use some very clever ideas that you should be able to follow with what you have learned in this course. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 57, Calculus, Redux.
We've now come to the end of our story. It's been a long and difficult journey, and I'm guessing you probably felt like giving up more than once along the way, but you didn't. You persevered, and you made it to the end. And now it's time to enjoy the fruits of that hard labor. In this lesson, we're going to slow down and take a reflective look at what we can and cannot do with calculus.
If we take a moment and think about all of the things that we have learned in this course, we see that there's quite a lot that we can do. We understand limits, derivatives, integrals, ordinary differential equations, and Taylor series. However, there are a few things that we can't do. And in this lesson, we're going to examine the boundary between what is possible and what is just beyond our reach. Let's begin with an example of a difficult integral. It is a fact that the integral from minus infinity to infinity of e to the minus x squared over 2 dx is the square root of 2 pi. Now you may ask, well, who cares about such a result? Well, you care about this result if you want to do anything in probability or statistics, because this is the result that says that a standard Gaussian is, in fact, a probability density function. So let's see if we can solve this using the tools that we've learned in this course. Now we know from the standard expansion for e to the x that e to the minus x squared over 2 is the sum over n of 1 over n factorial times quantity negative x squared over 2 to the nth. We know that this converges absolutely, and we know that because of that absolute convergence, we can integrate term by term. So let's try that. We can take this sum and integrate the individual terms. Reversing the integral and the sum, what do we get? Well, we get the sum over n of negative 1 to the n times 1 over n factorial 2 to the n x to the 2n plus 1 over 2n plus 1. That's great. But we have to evaluate that integral from negative infinity to positive infinity. That seems nonsensical. And in fact, that's not going to work. We have failed. Doing things term by term is not going to help for this improper integral. Here's a different strategy. Let's show that e to the minus x squared over 2 equals the limit as n goes to infinity of cosine raised to the nth power of x over square root of n. This is not so well known of a result, but it's very suggestive. It's as if you're taking the first lobe of the cosine function and stretching the base out to infinity while squeezing the tail down. Well, let's see, how would we prove this? If we denote by L this limit, then we could take the log of both sides. Assuming that we can reverse the limit and the log, then we pull down the exponent of n, and we consider log of cosine of x over root n. In the limit, as n is going to infinity, then x over root n is getting small, and we can perform a Taylor expansion of cosine about 0. That gives us the dominant terms, 1 minus 1/2 x squared over n. All other terms are big O of x to the 4th over n squared, and hence ignorable in the limit. So what do we get? We get that the log of L is equal to negative 1/2 x squared. That means that L is indeed e to the minus 1/2 x squared. Now, why might this be useful? Well, if we want to integrate this, going from negative infinity to infinity, well, it's a little bit better. I claim that it's possible to evaluate the limit of this integral, but it gets very delicate because we have to worry about the bounds and the fact that it's an improper integral and there's a limit. There's not enough room on this slide to give a proper argument. You have to learn a little bit more about how limits and integrals interact. So we've failed, but this integral is easy when you use the techniques that you'll learn in multivariable calculus. I guarantee you that you will do this integral, and it will take just a minute. Let's turn to a different problem that we can almost do. This one coming from ordinary differential equations. Recall the result with which we began this course, namely Euler's theorem that e to the it equals cosine t plus I times sine of t. Now, we took this as a given. We didn't prove it. How might you give a proof of something like this? Well, one obvious thing to do is write everything out in terms of Taylor series and show that the Taylor expansion for e to the it is equal to that of cosine t plus I times sine of t. However, you may recall that we used this result to derive the series expansions for cosine and sine, so that's a little bit of circular logic. What else could we do to try? Well, consider the following. If we let z be equal to e to the it, we're going to think of z as a function of t. Then there's an approach using ordinary differential equations, because the one differential equation that you know for sure is that e to the constant times t is the solution to the differential equation. Z prime equals that constant times z. In this case, the constant is I, square root of negative 1. Now, this shouldn't be too weird. Z of t is just a function. It now has a real and an imaginary part. Now, let's write out the real and the imaginary parts of z as follows. Z of t equals x of t plus I times y of t, where x and y are real functions. Now, what happens when we multiply this by I? Well, I times z equals I times x plus I squared times y. The I squared becomes a negative 1, and we can reverse the order so that we keep it real part and then imaginary. Now we know that z prime equals I times z. So what is z prime? Well, I can use the linearity of the derivative and say that z prime equals x prime plus I times y prime. And now my differential equation z prime equals iz really turns into a system of two differential equations, one for the real part that says x prime equals negative y, and one for the imaginary part that says y prime equals x. Now this is a system of two differential equations. There's no imaginary numbers in here. These are both real functions, but they are not independent. They are coupled. The x prime depends on y. The y prime depends on x. We have not learned how to solve systems of coupled ordinary differential equations. Now you might look at this and say, well, if x were cosine of t and y were sine of t, then this would work, since the derivative of cosine is minus sine and the derivative of sine is cosine. That's fine, but this is not a principled or systematic approach. That's just a guess. When you do take multivariable calculus, this will be an easy result. You will learn methods for solving systems of coupled linear ordinary differential equations, from which will follow easily Euler's theorem. Let's turn to one last problem that we can't do, this one involving series. It is a result that we've mentioned several times, that the sum over n of 1 over n squared equals pi squared over 6. You know that this series converges. You know how to bound the error for a finite approximation. But how do you show that the exact result is pi squared over 6? Well, let's give it a try. We're going to show as much of the proof of this as we can on one slide. Let's begin with the function u equals arcsine of x, and in a somewhat unmotivated step, we're going to integrate u du as u goes from 0 to pi over 2. When we do so, we get, of course, u squared over 2 evaluated at the limits, yielding pi squared over 8. Note the presence of a pi squared. That is a critical piece. Now, when we substitute in arcsine of x for u, we get the integral of arcsine dx over square root of 1 minus x squared. Changing the limits, this becomes the integral as x goes from 0 to 1. Now we don't want to evaluate this integral. We already know the answer. It's pi squared over 8. What we want to do is substitute in the Taylor series for arcsine of x. We've run across this once or twice before. It's an unusual looking series. The coefficients involve the products of odd numbers in the numerator, the products of even numbers in the denominator, and an x to the n over 2n plus 1. Now, this is looking rather complicated. We can integrate this series term by term, but integrating that x to the n over square root of 1 minus x squared is highly non-trivial. That is doable by the methods of this class. You can do it with integration by parts and a reduction formula. I'm not going to show you all of those steps. It wouldn't exactly fit on this slide, but trust me that when you do so, you will get, after a lot of simplification, the sum as n goes from 1 to infinity of 1 over quantity 2n minus 1 squared. That's so close to what we were looking for. This is the sum of the odd numbers in the denominator squared. Well, again, with just a little bit more of an argument involving a geometric series, one can show that that sum is 3/4 of the sum over n of 1 over n squared. And that sum of 1 over n squared is what we were looking for, knowing that this is really 4/3 times pi squared over 8 yields pi squared over 6. Now, you could certainly ask for a clearer or more complete proof. The one that I've sketched is due to Euler, the master himself, and it is, if my research is correct, his fourth published proof of that result. But it's certainly not easy. Now, you're going to expect that I'm going to tell you that this is easy when you learn multivariable calculus. Well, you may see a proof of this using multivariable, and it will be easier to follow than the one that I've sketched out. But I am not aware of any proof of this result that I would call easy. Some mathematical truths are deep, they are difficult, and they require an extraordinary amount of effort to ascertain. Some truths are right at the boundary between what we can do and what we can't, and they are worth striving for.
And that is the end. You made it! Congratulations! You got all the way to the end. It was a hard and long class, but you learned a lot. Take a moment, relax, prepare for the Day of Judgment, otherwise known as the final exam, and enjoy the fruits of your hard work.
Cut.
Oh, is that it? We're done? Yes! Oh, I'm so happy. Oh, thank God. Oh, good job, Jordan.
Thanks. You too.
I'm going to take a nap.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 57, Bonus Material. Well, that seems like a bad way to end the course, talking about what we can't do. Let's change things up a little bit. Go back to the very beginning of this class. That began with the question, what is e to the x? Well, by now, you all know exactly what e to the x is and means on so many different levels. But let's reconsider this question one more time from the point of view of discrete calculus. And what I'd like to emphasize is a particular point of unity between discrete and continuous calculus. This is Newton's formula, something that I've been saving for a special occasion. Let's begin. Recall that the forward difference operator, delta, can be expressed as the shift, E, minus the identity, I. If we rearrange terms a little bit, then we can express the left shift, E, as delta plus I. Now let's say that we want to shift over not one slot, but n places. Then we can express this operator as a power, e to the n, which thus can be expressed as quantity, delta, plus I to the n. Now what happens when we multiply that out? Well, we can use the binomial theorem to express e to the n as the sum, k goes from 0 to n, of the coefficient, n choose k, times delta to the k, times I to the n minus k. These binomial coefficients, you recall, come from, say, Pascal's triangle, or the definition in terms of factorials of n and k and n minus k and something like that. Anyhow, let's look a little bit more carefully. Recall that the identity operator, I, is the do-nothing operator, so we can effectively ignore it and just look at powers of the forward difference, delta. Now, remember, one of the useful formulae from discrete calculus is the notion of a falling power. N to the falling k is n times n minus 1 times n minus 2, all the way to n minus k plus 1. But this is related to the binomial coefficient as follows. N to the falling k can be expressed as n choose k times k factorial. Now that means that we could rewrite e to the n as the sum k goes from 0 to n of n to the falling k divided by k factorial times delta to the k. And at this point, if you've been paying attention in this class, you see something that looks slightly familiar. If we take a sequence, A, and consider the nth term, A sub n, this is really the shift, e to the n, applied to A, evaluated at 0 at the initial slot. That means that we can express A sub n as the sum k goes from 0 to n of 1 over k factorial times the kth forward difference, delta to the k of A, evaluated at 0 times n to the falling k. This is Newton's formula in a slightly different language than you'll find it in most books, but in the language of discrete calculus, a language that makes you see immediately the relationship to Taylor series. Indeed, Newton's formula is the discrete calculus version of our classical formula for the Taylor series of f at x. Let's look at the similarities. In both cases, we have a 1 over k factorial, and we have, in the discrete version, the kth forward difference of A, evaluated at 0. In the smooth version, we have the kth derivative of f, evaluated at 0. These look a little bit closer if we replace that kth derivative of f by the kth power of the differentiation operator, capital D, applied to f, and then evaluated at 0. Whereas in the smooth case, we have x to the k. In the discrete case, we have the discrete version of this monomial, that is n to the falling k. This beautiful and fearful symmetry between the notion of a Taylor series for discrete and continuous calculus is one of the gems in this course. If you don't mind, I would like to make a few observations here at the very end. Recall the shift operator, E, applied to a sequence A and evaluated at the nth term is really just A sub n plus 1. And in operator language, it can be expressed as I plus delta. There's a corresponding shift operator in the continuous world as well. E applied to a function f and evaluated at x is simply f at x plus 1. Now, way back when, we argued, using Taylor series, that the shift operator in the smooth world is really the exponentiation of the differentiation operator. That is, E is I plus D plus 1 over 2 factorial D squared plus 1 over 3 factorial D cubed, etc. And seeing the relationship between the smooth and the discrete versions of a shift lead us to a few interesting observations. First of all, from the observation that the shift operator is the exponentiation of the differentiation operator, we can express the discrete derivative, the forward difference, delta, as e to the d minus I. This gives us an explicit connection between the notions of differentiation in the discrete and the continuous world. Lastly, we could say that differentiation, d, is really the natural log of the shift operator, or if you like, the natural log of the identity plus the forward discrete difference, delta. Those are all beautiful observations, and all are connected to this simple initial question with which we began. What is e to the x? By now, you have seen so many answers to that question from so many different perspectives. But you haven't seen it all. Indeed, there is much more to mathematics than just calculus, even the type of calculus that you have seen in this course. I hope that this course has been for you more than a bag of tricks or formulae written into boxes. I hope that you have seen the beauty and the wonder that is implicit both in the world around us and the mathematics that we use to model it. I hope that this course has been for you more than just a few video lectures in which to up your skill set. Pay attention to the things around you. Go deeper. Maybe take a few more math classes to see more of what's out there. It has been my privilege and pleasure to be your professor this term.
This is Calculus. I'm Robert Christ, Professor of Mathematics and Electrical and Systems Engineering at the University of Pennsylvania, and you are about to have a dream of multivariable calculus.
You're having a dream, a very strange dream, in which the ghosts of calculus past come to haunt you, showing you series everywhere you see. The ghost of calculus future now comes to show you what you might see in multivariable calculus.
Calculus, as ever, begins with functions. Functions that have inputs and outputs. But in multivariable calculus, one considers functions with multiple inputs and perhaps multiple outputs. Such functions are common in so many applications, in dynamics, in market systems, in looking at digital images. Anything having to do with data will involve functions with multiple inputs and multiple outputs. How do we do calculus for such functions? All of those inputs and outputs can lead to notational complexity, but with the appropriate data structure, the story of calculus will remain the same. What is the right data structure for doing calculus with multivariate functions? The appropriate data structure is that of a matrix. A matrix is simply an array of numbers. For example, a 4x3 matrix consists of 4 rows and 3 columns. Certain matrices are especially useful in calculus. These are the square matrices. For example, a 3x3 matrix, or a 2x2 matrix, or even a 1x1 matrix, which you are used to thinking of as simply a number. Certain matrices have wonderful properties. For example, the identity matrix, often denoted as I, is a square matrix consisting of ones along the diagonal and zeros off the diagonal. Why is this called the identity matrix? This is connected to matrix algebra. One of the first tasks of multivariable calculus is learning matrix algebra. For example, you can multiply matrices together. We could take, say, a 2x3 matrix and a 3x3 matrix and multiply them together as follows. What one does is multiply the rows of the first and the columns of the second matrix. Through a particular manner, the first term in the first row is multiplied by the first term in the first column. To this is added the second term, the third terms, etc. So, for example, the first row of the matrix shown, 3, 1, 0, is multiplied by the first column of the second matrix, 2, 1, negative 2. The answer is 3 times 2 plus 1 times 1 plus 0 times negative 2, or 7. One fills in all of the other slots of the product matrix through a similar method. Now, in the end, there's some very nice properties to matrix algebra. The identity matrix is something like the number 1 in that it does not change a matrix when you multiply by the identity. Other matrices have similar interesting numerical properties. For example, consider the matrix A that is a 2x2 matrix, 0, negative 1, 1, 0. Since A is a square matrix, we can multiply it by itself. What happens when we square A? We will get negative 1s on the diagonal and zeros off the diagonal. That is, A squared is something like negative 1 in matrix algebra. So this matrix A is something like the square root of negative 1. You may wish to remember that little fact. As data structures, matrices work well with vectors. One way to think of a vector is as a difference between 2 points. One considers 2 points in n-dimensional space and looks at their difference. This gives an object that has both a magnitude, or a length, and a direction. For example, a planar vector has 2 components to it, the change in the x direction and the change in the y direction. A vector with 4 components is something that you might call 4-dimensional, and you might represent it as a column vector or an n-by-1 matrix. Now, vectors also have an algebra. You can add vectors together in a way that you've probably done before in geometry class by moving them head to tail and looking at the resultant vector. Of course, vector addition is commutative, unlike matrix multiplication, and it has some wonderful properties. Vectors relate to calculus by encoding rates of change in multiple variables. This leads to the first key idea in multivariable calculus. I want you to remember that the derivative of a function at a point is not a number. It is rather a matrix. When you have multiple inputs and multiple outputs, you can think of the rates of change of a particular output with respect to change in a particular input. These are called partial derivatives, and they are extremely useful in calculus. And why is the data structure of a matrix important? It is because the algebra of matrices mirrors what functions and their derivatives do. For example, the chain rule is manifested as matrix multiplication. This and other examples of matrix algebra are extremely useful in multivariable calculus. We also need matrices to solve systems of ordinary differential equations. When there are multiple variables, then we need multivariable calculus. Consider, for example, the simple system x prime equals minus y and y prime equals x, where x and y are functions of t. This is a coupled system. The derivative of x depends upon y. The derivative of y depends upon x. We can recast this as a matrix equation by defining a vector variable, capital X, that has x of t in the first slot and y of t in the second slot. Then what is the derivative of this vector, capital X? We can write that as a product of the 2 by 2 matrix A, 0, negative 1, 1, 0, with the vector x. This is the multivariate analog of the simple ODE x prime equals ax. But now, x and x prime are vectors, and A is a square matrix. What's the solution to this equation going to be? Well, we've seen an equation like this before. Let's see if the solution bears out the pattern. What I want you to remember is that the solution to x prime equals ax is the exponential, whether we're talking about scalars or vectors. Here, the solution is x of t equals e to the at times x naught, where As you may recall, x naught is the initial condition, in this case, initial conditions, since there's more than one variable. And what is e to the at? How do I exponentiate a matrix? Well, how do we exponentiate anything else? Of course, we do so via a series expansion. Since A is a square matrix, you can take it to the second power, the third power, the fourth power, etc. The exponential of a matrix A, e to the a, is 1 plus a plus 1/2 a squared plus 1/3 factorial a cubed, etc. Oh, wait a minute. What do I mean by 1 at the beginning? I mean the identity matrix, I. And so the solution to our differential equation involves multiplying the matrix A by t and then exponentiating this. This is the solution to our linear system. Remember this. You will see it again someday. Now, of course, calculus doesn't end with derivatives or differential equations. We still have the notion of integrals to worry about. You've already seen a little bit of what will come in the sense of multiple integrals, double integrals, triple integrals, or even more. Without going into any details, the one thing that I want you to remember is that when you're integrating and you want to do u substitution, you're going to have to use derivatives. That means you're going to have to understand derivatives and the matrices associated with them very well. If you have a vector of variables, x, and a new vector of variables, u, that is related to x by some function, then what is du? What is dx? And how are they related? Here's a hint. It has something to do with matrices and derivatives. Remember, you'll see this change of variables formula again. The last set of grand ideas in multivariate calculus concerns fields. We'll begin by looking at vector fields. A vector field is an arrangement of a vector at every point in space. Such objects model, say, the motion of a fluid or certain quantities in electromagnetics. How would you talk about the derivative of such a field? What does it mean to differentiate a field of vectors? How do you integrate with respect to a vector field? What does that even mean? We'll spend a lot of time answering those questions. What I want you to remember when you see multivariate calculus is that it tells the same story as single variable calculus, only with a few new characters and data structures and a lot more action.
I hope that when you do take multivariable calculus, that you remember having had this wonderful, weird dream about what multivariable calculus is, how it follows single variable calculus, and how important the subject is. Till then, sweet dreams. I'm Professor Geist, and I've been your professor for this calculus class. I'm so proud that you've made it to the end, and here, at the end, I'd like to introduce to you some of the people on my team who've made this course possible.
My name is David Lonoff, and I'm a PhD student in mathematics at the University of Pennsylvania, and I was the chief editor of the PennCalc Wiki. Thank you for taking this course, and thanks to all of you for reading the wiki and giving me suggestions.
Hi, everybody. My name is Alberto Garcia Raboso. I'm a PhD student in mathematics here at the University of Pennsylvania, and I have been responsible for most of the homework problems in this course. I hope you enjoyed them, and I want to thank you for working so hard on them and for participating in the discussion forums. Good luck with the final exam.
Hello everyone. My name is Radmila Sazdanovic, and I'm a postdoctoral fellow in the Department of Mathematics at the University of Pennsylvania. For this course, I was helping with the homework and quiz problems. I hope you find them helpful, challenging, and enlightening. Thank you for taking the course, and best of luck on your final exam.
Hi, my name is Vidit Nanda. I'm your lead TA for this course. You might know me from the solution manuals to the quizzes. I wanted to say thank you for all your hard work, and it's been a pleasure being a part of this course. All the best for the final exam.
And I'd like to also give a special thanks to my family and everyone who worked behind the scenes to make this course possible. And thanks to you for sticking with it, working hard. Good luck studying. Do well on the final exam.